Видно и слышно, можете говорить.
Dear colleagues, hi. I'm Olga Sokolova. I'm professor of Russian Academy of Science, and I'm really happy that we are opening the third Russian Cryo-EM conference in Moscow. Today there's a sunny day in Moscow, but pretty cold, and it's usual at the beginning of summer. But actually we don't care much about weather because due to COVID-19 pandemic, we have to meet today online. But we are lucky because we have a great lineup of speakers for our conference. We have already more than 600 participants that have been registered, most of them virtually and from different parts of the globe. And this probably would not have happened if we have held face-to-face conference. So Zoom conferences are the great relief nowadays. So despite current medical and political reasons, we structural biologists, we will stay united and perform a great science, which we will share with our students and postdocs. So this conference is organized jointly by Moscow Lomonosov University and Research Center of Biotechnology, Russian Academy of Science. So Dean of Biological Faculty, member of Russian Academy of Sciences, Professor Mikhail Kirpichnikov, kindly agreed to say some words to the participants of the conference. And I invite Professor Kirpichnikov now.
Dear colleagues, dear invited speakers and the participants, I am pleased to welcome to you to the third International Russian Conference on Cryo-electron Microscopy. This conference organized by Moscow State University. The high-performance technology of cryo-electron microscopy allows to obtain the three-dimensional structures of proteins and their complexes. The achieved resolution by now is comparable to crystallographic, which is from 1.5 to 3 angstroms. And information obtained by cryo-electron microscopy is much more valuable because it gives an idea of the natural topology of biomolecules. And in the last several years, this method has dramatically changed the importance of structural biology for researchers, not only in the field of molecular biology and biochemistry, but also in pharmaceutics, organic chemistry, physics, and materials science. International scientific cooperation is an important part of our university life. And I'm sure that the conference will be one of the most exciting scientific events held in MSU in 2021. This conference has already become a regular event, attracting scientists from over the world. This year, due to the COVID-19 pandemic, many invited speakers could not be present in person, but our technical staff worked hard, and this allow for online presentations. It is very important that undergraduate students and graduate students from our university participate in this remarkable event. As Dean of Biological Faculty, I wish you a great time at the conference, and good luck to everyone.
Okay. Now the president of the Research Center of Biotechnology, Russian Academy of Science, member of Russian Academy of Science, Professor Vladimir Popov, would like also to greet our conference participants. So you are welcome, Professor Popov.
Thank you. Good afternoon, or probably good morning, or probably even good evening. Dear colleagues, dear friends, on behalf of the administration of the Federal Research Center of Biotechnology of the Russian Academy of Science, on behalf of all the scientists of the center, I would like to welcome you at the Russian International Conference on Cryo-electron Microscopy 2021. We at our research center are very happy that we could assist in the organization of this exciting event and provide the premises of our institution as a venue for the conference. We look forward for the 4 days of the exceptional quality lectures of the most distinguished scientists, fruitful discussions, and amusing socializing. Structural biology is one of the pillars of the modern biology, and cryo-electron microscopy is the very forefront of this research area. The current COVID pandemic, that unfortunately is still with us, gave a good example how the advancements of the fundamental research can materialize into new medications, vaccines, and therapies. Just a few weeks after the virus has been isolated, the first structures of the viral proteins complexed with its targets have emerged, paving the way to the development of the strategies to counteract the disease. It is a very good example of the impact of the modern science and technologies that power it on our everyday life. RICCEM 2021 is the first conference in 18 months that is not totally virtual. We missed very much all this time the personal contacts, socializing that make such events so interesting and fruitful. I'm sure that RICCEM 2021 will be a success and will provide an additional impact to the development of this exciting structural technology. I hope that hosting of the conference at our research center will boost an interest in Cryo-EM among our staff, in particular among young scientists, and will lead to new fruitful and beneficial collaborations. I wish a conference a success, and for those who have chosen to come to Moscow in person, an interesting social agenda. Moscow now is a very nice place to visit and provides a lot of attractions. Moreover, that the weather forecast for the next week is not that bad. Good luck, everybody, and I pass the floor now to Dr. Olga Sokolova to proceed with some technical details. Thank you.
Okay, thank you very much, Professor Popov. And now I would like to touch some practical aspects of the conference that we, especially those who are participating in person, need to know. So the first day of the conference, which is today, will be held online only, but at the evening, we invite those of you who are in Moscow to the traditional welcome party at Moscow University Botanical Garden. So there should be no rain, and despite the cold weather today. Starting from tomorrow, our conference will be in hybrid format. We invite all offline participants to the Research Center of Biotechnology, where we will start our first lesson with the offline talks. So all talks, both offline and online, will be streamed on YouTube. And every day you will have a new link to the lectures, and this link will be, you can access it by clicking on live stream button on the conference front page. Also, we will have a poster session. So right now, all posters are already available on our website under the tab posters. So you can press on this tab and look at the posters. And then when you will be ready to, the poster session will be held online on June 1st at 6 p.m. Moscow time. Then you would be able to enter the special meeting room and ask questions for the people who presented these posters. Also, the virtual book of abstracts will be available on our website. If you click on our website onto the tab abstracts, you can see all abstracts of this conference. The abstracts which we obtained by the deadline, they will be published as a supplement to the June number of International Journal of Biomedicine. And now I think it's time to start our first plenary lecture. Okay, so our first invited lecturer is Professor Richard Henderson from MRC Laboratory of Medical Biology, Cambridge, United Kingdom. And I think all of you know that Professor Henderson is a pioneer in the field of electron microscopy of macromolecules. So we're very happy that we will today hear this lecture of Nobel laureate Richard Henderson. So you're welcome, you can start your lecture.
Okay, so Olga, thank you very much, and thank you for all of the people who've organized it. I hope everyone can hear me.
Yes.
Good. So first, I'm sorry, I had been looking forward greatly to visiting Moscow to come to the meeting. So I'm very sorry to be here in Cambridge rather than in Moscow. Secondly, it's a great honor to be the opening speaker at such a great meeting, 4 days with many good speakers, which I look forward to hearing. So in my talk, I thought, since I'm starting, I should begin with a little bit of background about Cryo-EM before getting to my main message, which is about how to make electron cryomicroscopy, which is in a very strong growth phase, how to make it much more accessible and able to expand at least in the next few years. So I'd like to begin by showing the first slide, which is a slide that Tim Baker and I made in the year 2000 when the International Tables for Crystallography had a volume F, all to do with macromolecular structure determination, organized by Michael Rossmann and Eddie Arnold, and most of it was about electron microscopy, but Hua Chu and I each wrote chapters about electrons for diffraction and imaging, and as you notice, Hua will be speaking about this later towards the end of the meeting. So in the review that Tim Baker and I wrote, we thought we needed to give an overview, which is still topical, of what Cryo-EM involves. And what we have here is 4 different types of specimen, single particles without any symmetry in ice, and this was 70S E. coli ribosomes from the work of Joachim Frank's group. And in the year 2000, you could reach about 11 angstrom resolution with, of course, it's much better now. And Joachim will also be speaking later. The second image is single particles with a lot of symmetry, which makes it easier to get to high resolution. And this structure, the hepatitis B virus cores, was Bettina Botcher's work as a postdoc, and she was the first one to get below, with single particles, below 1 nanometer resolution, so 7 angstrom resolution. And then the third panel is helically arranged structures, and this is the thin filament from muscle decorated with myosin from the work of Ron Milligan. And even though in late 1990s it was only 30 angstrom resolution, they were able to see the actin core in blue, tropomyosin in green by doing difference maps, and then the 3 of the domains of myosin attached to the actin in the pink, orange, and yellow. And of course, again, these are much higher resolution now. And then the last panel is an example of a 2D crystal from Werner Kuhlbrandt's work when he was at EMBL on the light harvesting complex from green plants. And there are now 8 or 10 high resolution structures from 2-dimensional crystals. So this was essentially no order, 0 dimensionals, 1 dimension, and 2D. And of course now you can do, wasn't so topical in the year 2000, but you could do electron tomography and get into 3D without any ordered structures. So that gives you a good overview of where we were 20 years ago. And one of the reasons that the method has been so successful came from the work Jacques Dubochet's group did at EMBL in the early 1980s, where they developed this plunge freezing method with a grid onto which you put a small sample, 2 or 3 microliters, and then blot it, and then drop it into a liquid ethane container at liquid nitrogen temperature, either under gravity or with a spring to help it. And this is really a method that's been going now for 40 years. It has a lot of advantages. You blot off any material on the surface, you get a controlled thickness of film, and of course there will be better methods coming, but for the moment this was a really big breakthrough. And one of the earliest pictures that Dubochet's group took was this picture of adenovirus, which was on the front cover of Nature in 1984, and it shows these 1000 angstrom diameter particles, slightly fuzzy because in the 1980s the electron microscopy resolution wasn't so good. It's 100 kilovolt acceleration and tungsten filaments, so not very spatially coherent. But you can see the thin film has preserved many of the viruses very nicely. A few of them have broken up, probably by interaction with the air-water interface, and you can see a few black dots, which are some of the subunits that have fallen off. Obviously the preparation was nice before it was blotted, and so this is one of the problems still going forward. And then that was 1984, but it took until 1991, 6 or 7 years, before those types of images were converted into knowledge of what that 3D structure was. And that was the work of Phoebe Stewart here, also at EMBL, then working in Steve Fuller's group. And with this technology, that quality of image, she reached a resolution of 35 angstroms in 3D. You can see the subunits, but not much more, the spikes perhaps. And then another 20 years passed before the methodology and the microscopes got better. And this is an image from Hong Cho's group, published in 2010. The same virus recorded on the same detector photographic film, but now with a 300 kV microscope, better vacuum, and a more coherent field emission source. And now you can see a lot more detail inside the structure of each of the viruses. And when these images were processed, the same image on top left, you can see that Hong Cho's group got a resolution of 3.6 angstrom resolution, so a 10 times better resolution, 1,000 times more data. And of course, instead of a few dozen images on film, they were now taking a few thousand images on film, but still on film. And you can see that they've reached a resolution in the maps consistent with what the computer estimates. Here are 3 parallel strands of beta sheet, and you can just about see side chains coming out of it. So that was an advance that came from the technology. And then round about 10 years ago now, the first new types of detector, better than film, came in. And this was a paper that Greg McMullen and we in Cambridge did in a comparison of 3 of the new electronic detectors in which the electrons go directly into the detector are compared with film, measuring the detective quantum efficiency as a function of resolution, and 1 times Nyquist means that the maximum resolution that you can get with that sampling frequency. And this was the Gatan detector that was the first one that could do counting. The now Thermo Fisher Falcon detector, which in this graph is it with an integrating mode rather than counting mode, and then Direct Electron, Southern Californian company. All of them are better than film, and all of them are reading out many times per second, from tens to hundreds per second. And so the resulting movies that you get, rather than one image on film that you have to develop, fix, dry, and scan, you get immediate impact, and you get a movie which, because of one of the problems is beam-induced specimen motion, gave you a second advantage. So one advantage was the higher DQE. The second advantage was you could get rid of a large proportion of the beam-induced specimen motion and get better data. And so now I'm just going to give you 5 structures that I think illustrate the best aspects of the power of the Cryo-EM. And the first one comes from Alexei Amont's work when he was a postdoc here with Venki Ramakrishnan. He collaborated with Xiaochen Bai in Shor Sherez group, and they took images of this bovine mitochondrial ribosome in which you see all the particles, using the software Relion that Sherez started to write around about 2010. They were able to get the average structure from all the particles, but also using one of the features in Relion, which is 3D classification that Shores had worked on earlier using the XMIP system from Madrid in Spain. They're able to distinguish between some of the particles in this collection of images of ribosomes that came from bovine mitochondria, but are not completely pure. Alexei had been trying to crystallize it. It never crystallized. It was because it's maybe only 80 or 90% pure, and the impurity is often the cytoplasmic ribosomes, which have a quite completely different structure, similar but different. And so by 3D classification, they could then separate them into some of these particles in the same images, the same data set, are the cytoplasmic intact ribosomes. Others are the mitochondrial one that was his target. Some of them are fully intact. Others are just the heavy subunit, the large subunit. And so by selecting out the particles from the same data set that describe the structure they're interested in, they're able to get a better structure for the target structure. And then also another of the features in Relion and in other of the softwares is that you can then mask out in these images from an initial 3D model the part of the structure that you're most interested in, for example, the large subunit, and then do the positional and orientation alignments based on that, and then get a much more accurate and sharp map of the part you focused on. And then in the same data set, you can then focus on another part of the structure, a small subunit, get a nice map of that. And by doing that, they were able to get a complete description of all the RNA and all the protein molecules in the mitochondrial ribosome that had been resistant to all efforts prior to that. And here's an example of some of their density map, a little bit of Watson-Crick RNA double helix, a top view of one of the base pairs, an alpha helix, and then 2 either beta strands with a turn, and then one that they believed was a magnesium ion. So really good quality maps. Estimated resolution 3.1. The density that you look at agrees with that density. And so this shows a lot of this one structure shows a lot of the aspects of Cryo-EM that makes it such a desirable method. So the next structure came from a specimen that Judy Hurst, who's now the director of the MRC mitochondrial biology unit in Cambridge, about a few hundred yards from the lab here, and she had heard about the progress of Cryo-EM and brought this sample over that had been made by Jaipen Ju in her lab, and then Vinoth Kumar in our lab took images like this, and after a very short time got this map initially at 5 angstroms in 2014, showing 8 iron sulfur clusters at a high contour level, and then the structure at just 5 angstrom resolution showing 76 transmembrane helices, and then at a lower contour level still the detergent lipid belt around it. And then with a little bit more work they were able to go on and get a higher resolution structure, and then built with help from the core subunits. There are 16 core subunits in blue that came from the work of Leo Sasanoff, and Leo of course now does great work also on other types of complex 1, and we'll be hearing about that later on. But this was another good example. Couldn't be crystallized, or parts that were crystallized were not the whole structure. Then a third one came from work of Miriam Koshai, who was a PhD student with Radostin Danev and Wolfgang Baumeister in Martinsried, and she decided, it was her idea, to take images of human hemoglobin, which is in the top left panel, with a little bit of extra help from the Volta faceplate that Radostin Danov had been developing at Martinsried, but he had a 10 or 20 year history of working on faceplates, so that helped a lot initially in looking at images of such a small 64 kilodalton structure. And she got these 2D classes, helices, and a nice structure of the heme group in hemoglobin, just like the images that Max Perutz and his collaborators had got maybe 45 years earlier with the heme group and the distal and proximal histidines. So a very good example of the range of structures that you can do. And then just 2 more. One is that the use of Cryo-EM has spread to the pharmaceutical industry. They were alert to the possibility that once the resolution got high enough, they could then do the same kind of structure-based drug design that they'd been doing using crystallography for about 25 years and so on. And this is a publication from the Astex company in Cambridge, and Pamela Williams was the leader of this work, and this was not one of their drug targets, but it was a test structure, beta-galactosidase, that we'd worked on earlier. Sriram Subramaniam has done really good work on that too, and his group, Partisagi. What they did was to collect lots of data on lots of different ligands and show that in these 3 panels here, there were beta-galactosidase with 3 different bound ligands. You can interpret how they're binding, find the environment, and then if you were planning to do an improved drug design for a beta-galactosidase inhibitor, you'd have all the data that you needed to do intelligent drug design. And then they had another real target that they were working on as an anti-cancer drug. And so now there are a lot of companies. 5 companies in Cambridge got together about 4 years ago and invested in the Cryo-EM. And now there's a pharmaceutical consortium in Cambridge with 2 of the Krios 300 kb microscopes, and then all of these companies have now bought their own equipment. So it wouldn't surprise me if actually the investment in hardware for Cryo-EM in and around Cambridge, that the companies have actually bought more microscopes than the academics. So then the last one that I'd like to show, and you'll be hearing from Dimitri Lyunkis later, but I show this because it was the first time that anybody using Cryo-EM had collected good enough data at high enough resolution to show that the very slight E-volt sphere curvature that you get with the wavelength of electrons being at 300 angstroms, 0.02 angstroms, gave you an ability to improve it by doing an E-volt sphere correction. And so their title was Sub 2 angstrom E-volt sphere curvature. This was their images of adeno-associated virus. In this, Tan et al. And Dimitri took all the precautions that other people had noted that were needed in order to get to high resolution, and got this really nice map, initially at 1.9 angstrom resolution, with a B factor describing the fading of the data with resolution of 60 square angstroms. But after doing the E-volt sphere correction, which is had been built into the FreeAlign software since about 2005, 2006, Matthias Wolf was involved with that, they got a slightly higher resolution, very significant, although it doesn't seem much, 0.1 angstrom higher resolution, but with a B factor reduced from 60 to 50 square angstroms. And then of course you see all the nice side chains in terms of the resolution that you get here. So okay, so that is a kind of overview of where we're at, and tells you a lot about the power of the method. An overview of the whole field is in the next slide, which shows a comparison of the growth in depositions in the protein data bank over the last 20 years. You can see X-ray crystallography started very low, but is on a linear growth phase, whereas the Cryo-EM depositions, which is in this dark blue, is still in an exponential growth phase. And then the NMR, which peaked in 2007, is now used for other things rather than de novo structure determinations. And the comparison we like, in order to look ahead and decide what are the sorts of new equipment that we need for the future, is to plot the ratio of the number of PDB depositions made each year by X-ray crystallography and by EM. And you can see that in the year 2000 there was about 1,000 times more annual depositions. So very few high resolution structures, or structures that gave you coordinates. Then with the better microscopes, field emission guns, automation, high vacuums, it dropped to about 200 or 300 to 1. And then in 2012 to 13, these new detectors that I mentioned started to become available. Only 2 or 3 labs had them in the beginning, so there were only a few structures. But now, as investment and delivery has grown, you can see it's growing. And this straight line on a log plot means and then today, for example, the number of depositions that are made is by EM this year is just over 1,000, and by X-ray crystallography nearly 4,000. The ratio is 3.7 now, dropping from 100. And actually, of course, as you go on, the numbers get bigger and it becomes harder because you have to deliver more microscopes, people have to work harder and so on. But anyway, it's a good indication of where we are. And then if you try to extrapolate, you get that there'll be about 50-50 in sort of mid-2024, and then provided that enough microscopes are available and enough people decide to use them, then you'll be into an era where the Cryo-EM actually produces not just a lot of interesting structures that are not doable by any other method, but actually numerically more. So then we come to the sort of crux of the talk, which is it's basically to do with what do you do, where do you put your resources, what should we encourage the companies to invest in so that we can buy the right things. So here are some outstanding issues and obstacles to further progress. It's always a good thing to have bigger, better and faster detectors, because if you could make a detector that has twice the area or twice the speed, then you would need only half the number of microscopes to do the same amount of work. And then I'll come to this later, but the high voltage microscopes are expensive, and you could imagine having some less expensive microscopes. Perhaps one of the attributes would be that there would be lower electron energy. And then a second outstanding issue is many people have noted, for example, I just read an article in Science about the melanocortin 4 GPCR in complex with trimeric G proteins from Israel, and they used 10,000 images to get a 3 angstrom resolution structure. Beautiful structure, but a lot of work. So why do so many Cryo-EM structures start with millions of particles and then get rid of them, just like I was showing you with the that mitochondrial ribosome work, whereas theory says you should only need 1 or 2,000, and in cases of favorable specimens you can get high resolution with much fewer images. And so some of the reasons, there's a multiplicity of reasons, and all of them, to solve them, involve you getting involved with day-to-day work on solving the problem by making grids and looking in the microscope. So you need access to the microscope daily. So among those are denaturation, unfolding disintegration at the air-water interface, preferential orientation, perhaps caused by the surface, aggregation, why it aggregates when you do the plunge freezing. In some cases, it's not known. Of course, there are impure preps, mixed states, different conformations, and for that you do need the data. And then there are not really very good analyses. There's a few. Imprima from Frankfurt had one on the fatty acid synthetase, but some of the molecules can be distorted in some ways, and that would be useful to know. And then finally, in order to work with low concentrations, it would really be nice to have grids that had surface derivation, just like you have with affinity columns. So there are many things that need to be done, and one question is, how do we get to that stage without investing enormous sums of money in equipment? So the next slide is essentially the title of the talk: what is really necessary for excellent single particle cryo-EM? And of course, as the history of the field developed, at each point in time, a different problem was the rate limiting step. So for example, in the 1980s, the cold stages were very bad. You couldn't get beyond 7 angstroms because the cold stages were no good. Then the coherence of the field emission of the tungsten filaments wasn't good enough, so field emission guns had come in. High voltage was important, microscope vacuum was important, but now that we know it works, we can go back and ask what's really important. And this is so, you do need a good stable column. You can't have images drifting around or vibration. You can't have ice contamination. That was an early problem. We think less than 7 angstroms per hour makes it usable for, let's say, a day. And in order to do that, you need a reasonably good level of vacuum or a very good cryo shield. And then the field emission guns are 500 or 1,000 times brighter, and that allows you to do a much bigger defocus, see contrast at low resolution, and still get high resolution. And then the temporal coherence, the energy spread of the source, is very important. And this 0.8 electron volts in the field emission gun is about 3 or 4 times better than what you get with a tungsten filament. And of course you can have a monochromator, that makes it important as well, but you do need a stable column and a field emission source. These are essential. A small chromatic aberration coefficient is useful because that allows you to go to higher resolution given the energy spread of the source. And so I've written down here, so 2 millimeters CC coefficient at 100 kV or 4 millimeter. The spherical aberration doesn't matter because you're defocusing anyway, and spherical aberration is just a modulation of the defocus. You do need a really good detector. So, for example, the big breakthrough between film and CMOS, the direct electron detectors, was only roughly a doubling of the DQE, although there were movies with it, at low frequency, and then maybe 3 or 4 fold at high resolution. And then, of course, the larger the area, the better. So you do need a detector, whatever voltage you're going to use, with as high a DQE as possible at all resolutions. And then, of course, it's very nice if it's easy to use, so that you don't need to go on a 1-year training course in order to use it. You'd like to be able to walk up to it and use it. So to make it easy to use, fit it into a normal room so you don't have to build a special building to put it in, not too demanding on that. So these are all things that are essential or desirable. And then if you want to do slightly better, there are things that would be nice to have in future. We've had the Volta faceplate from Radiston Danev's work and Thermo Fisher, gel and so on, but it has some problems, and getting a really good one, and there is this on the horizon, there is this laser ponderomotive retardation faceplate that Holger Muller and Bob Glazer's groups have been working on in Berkeley. Monochromator or zero loss energy fit is very useful, and CC corrector. These are the top ones, are the desirable ones. So our idea of 4 or 5 years ago was to advocate that the manufacturers should consider the possibility of making the microscopes less expensive by adopting perhaps a 100 kilovolt platform with a field emission gun. And of course you can buy more expensive microscopes that have higher electron energies, 200 or 300, you can turn them down to 100 kV, but that doesn't fit with the idea of making it less expensive. And then the problem, even if you do that with an existing microscope, is that these direct electron detectors that I mentioned before, so DE, the Gatan K2 and K3 and the Falcon series, they were all designed to work really well at high voltage, high electron energy. And they work better and better. If you go up to 300, 400, 1 MeV, they'd work perfectly because they're very thin and the electrons go straight through. But they're not thinned enough that 100 kV electrons go through. So you need a different design for a lower, and we don't really have that, at least not in a big area at the moment, but I'll come back to that. And then obviously one way around getting good vacuums has been to make the loading system quite complicated and have multiple grids, but that does mean it takes still about an hour to put a sample in. So if you're screening for different conditions, you can't really have a turnaround. Even if you own a complete 300 kV Krios or JL arm that belongs to you, you can only do 2 or 3 turnarounds per day because the specimen loading takes a lot longer. And so the two systems that I thought I'd end up my talk by mentioning, and there will be a talk later on about the Tundra from Thermo Fisher, and the one that we've decided to adopt in Cambridge is to try and build on the gel column. So 2 more slides. One of these comes from before that's going to be the end of the talk. I've got 4 or 5 slides in between. So I wanted to go back now, before coming to this proposals for affordable microscope. I wanted to go back to a paper that I published as a review in 1995 in Quarter Reviews of Biophysics, where I compared, just from the literature, the cross sections for elastic and inelastic interactions for electrons. And elastic is what gives you the high resolution images. Inelastic is which deposits energy and does radiation damage, breaks bonds, causes ionization. And the ratio between elastic and inelastic tells you how much data you get out of your sample before you destroy it. And in this review, the comparison was with electrons with X-rays. And so again, here is X-ray inelastic radiation damage and elastic scattering, and also we did neutrons. And the bottom line was, when you add up all the numbers, that for each useful elastic event that contributes to your high resolution image, electrons are over 1,000 times less damaging than X-rays, and then for normal samples 3 or 4 times less damaging than neutrons at these wavelengths. So that was the purpose of the review. But now that we're looking to make smaller improvements and looking to see what is really essential for electron microscopy, it's useful to look back at this slide. And I've put on this new circle here with the elastic and inelastic cross sections at 100 kV. And you can see these 2 lines, as you go to lower energy, they get closer together. And actually at higher energy, the inelastic goes up because there are various other energy deposition mechanisms. But we decided, and this is Chris Russo's group, Matthew Peat, a couple of years ago, that we need to, before making any plans, we need to reinvestigate this region of electron scattering, both the elastic and the inelastic. And so Matthew Peat spent quite a while measuring, and this is the elastic versus energy, the elastic cross section, and he did this using diffraction from graphene monolayers, elastic scattering, as a function of the different energy. So this is beta squared v squared over c squared, and that the ratio of 100 kV to 300 kV is 2.01. Here is the 100 kV cross section for elastic, and here is the 300 kV cross section for elastic, and you can see 85 to 42, the ratio is 2.01. This is what it should be according to the well-known theories. And then if the curves get closer together at lower energy, the inelastic ratio should be less than this. And so the next slide shows our efforts to measure the radiation damage for paraffin or purple membrane, different resolutions, and here is the number of electrons that are needed to cause fading of the pattern to 1 over E at using 100 kV electrons and using 300 kV electrons. And if you look at the ratio here, it's 1.5, 1.6, and the overall average is 1.57. So that fits exactly with those theoretical and, based on experiments, the older curves in the literature. So this then is the main figure from this paper by Matthew Peet et al. About 18 months ago, that were doing a re-examination in the region of 100 to 300 kV of the theory behind elastic and inelastic scattering. And I have to move this. Sorry, I've got a blockage in my screen. So in addition to the ratio of elastic to inelastic being the key factor, and these dotted in full lines that are in orange or in black are the same two curves that you saw in that review from 25 years ago, but this part has been remeasured and confirmed to be in exact agreement. So now we're going to compare again 300 with 100 kV, and the actual change in the ratio is it's a 28% advantage at 100 kV in terms of the amount of information you get for the same amount of radiation damage. However, in the sample, you have to have it thick enough, the thin film of ice by the Dubochet plunge freeze method has to be thick enough to contain, for example, a ribosome 250 angstrom SIPs. You need usually 300, 400 angstroms of ice. Although smaller structures, you don't need such thick ice. And so what we've done here is to work out the transmission from from electrons that are lost by mainly inelastic scattering. They're lost and they're no longer properly focused, according to the thickness divided by the mean free path. And so these broad dashed lines then are for three thicknesses of ice: 100 angstroms of ice, 300 angstroms of ice, 1000 angstroms of ice. And we're multiplying the transmission by the ratio of elastic to inelastic, and you get these curves. And what it shows is that for a 300 angstrom thick thin film of ice with your protein or virus molecules in it, the peak in the signal that you get occurs at 100 kV. And it's only if you get much thicker ice that the peak occurs at 300 kV. And there's a graph at the top showing you different thicknesses where the optimum is. And actually the vast majority of structures we're interested in are not bigger than 250 or 300 angstroms. They're smaller than that. And all the drugs that drug companies are designing, they're all smaller than that. So that suggests then that not only might 100 kV microscopes be less expensive to manufacture because they're smaller, there's not high voltage supplies and so on, but also the images that you get might be better out to a certain resolution until you get limited by the energy spread. Okay, so that's the bottom line. So we thought maybe we might have missed something. So in a paper that was Katerina Naida-Danova and collaborators, again, Chris Russo's group and our group were involved, we collected data on several different specimens at 100 kV using a detector that had been developed for X-ray crystallography by Dectris, so a hybrid pixel sensor, which was the only one that gave high DQE at the moment, although other people now and other organizations are working on making better 100 kV detectors. And this was the best structure that came out. This is DPS, and there'll be another talk in the meeting about DPS interacting with DNA. And it was a 3.5 angstrom resolution structure taken with less than a day's data, showing you that the 100 kV might be a good target to make an affordable microscope. It might give better data, and it works in practice so that there aren't any hidden problems that we haven't anticipated. So now we come to this tundra and gel. So this was a launch that Thermo Fisher did on the 18th of November last year, announcing that they are going to make a 100 kV screening microscope that initially will have only a phosphor fiber optic detector on it, their CETA-F, and we'll be hearing about that during the meeting. later on. But that's been announced. I believe you can order it, but you can't quite see it yet. It's still in development. And then my last slide then is what we've been doing in Cambridge, because we didn't think the companies were going to do it. And so we asked for grants and for support, and we've had support from Astex, the company that I showed data from Pamela Williams in Cambridge, from AstraZeneca, and from the Wellcome Trust to show proof of principle in an ordinary lab that you can do good cryo-EM without having to spend too much. So this is our JL 1400 column with this dexterous hybrid pixel detector on it. And these are 3 cold stages that we've bought from Gatan, Fiscioni, and Simple Origin. And what we don't have at the moment, we do not have on this microscope a field emission gun, but a company in York Probe Sources, has been designing and has developed one that we hope will be on this microscope quite soon. And so we're hoping that within a year or so, perhaps labs that don't have 3 or 4 million pounds or euros to buy the current state-of-the-art microscopes might be able to invest through JL or through Thermo Fisher into an affordable, good quality microscope that will still be a little bit less automatic than the high-end systems, but eventually might point the way forward for future developments. So I'm going to finish now by just with the acknowledgement slide, and what I did is to pick 5 structures. The historical one on adenovirus from Jacques Dubochet's group, Phoebe Stewart and Hong Cho. The mitochondrial ribosome from Alexei Emmert's group, Complex 1, that Judy Hurst and Vinod Kumar did. And what I didn't have time to mention is that all these people who did this work now are all around the world running their own groups. So Alexei's in Stockholm, Vinod is in back in India, Xiaopeng Zhu is back in China, Miriam Koshai works for Novartis in Switzerland. This is the Astex group doing structure-based drug design in a company, and then you'll be hearing from Dimitri later on. And then all our work involving detector developments, we've been doing this for maybe 20 or 30 years, was led by Wazi Faruqi, who originally worked on X-ray detectors with Hugh Huxley for muscle kinetics. Renato Turchetta and Nicola Guarini were the people behind our involvement in the original work that became the Falcon with Thermo Fisher. Renato now has his company in Barcelona. Nicola now leads the group at Rutherford Appleton Lab. And then Greg McMullen is the leader of that work here. And then Chris Russo, who's been involved in all of this work on the 100 kV with the grants and so on. And Matthew Peet and Katerina Naidianova are the 2 people doing that work in Chris's group. So I'll stop there, and hopefully it might be possible to have answer 1 or 2 questions. Thank you.
Okay, yes. Thank you very much, Richard, for very interesting talk. And yes, it is a pity that due to pandemic, you could not come to Moscow in person.
Yeah.
And we hope that in 2 years from here for the next our meeting, the epidemic situation will improve, and then you would be able to come in person, and we will wait for your visit. So right now we have a couple of questions. So first question from YouTube, what would be the role and impact of cold emission guns at 100 kV microscopes, and how much they will be more expensive?
Yeah, okay, so I think the question is, what about, so we have focused, my focus in this talk has been on how to open up the field so that we can make the development of specimens that give high resolution quicker, and how can you open it up also so that people who don't have so much money can do electron microscopy. However, many people in the field are very interested in the cutting edge, how to push the resolution to higher. And there will be a talk later on again by someone from Thermo Fisher on the Selectris and the Falcon 4, and both Thermo Fisher now and JL for many years have had cold field emission guns. And so if you're interested in high resolution, obviously you need to work at the energy spread for chromatic aberration, either with a monochromator or a cold field emitter. But the things that give you the big steps forward in order really are going from tungsten to a Schottky field emission gun gives you a factor of 4 reduction in the energy spread. And delta E over E, the energy spread ratio, as you improve that, make it smaller, your resolution goes up proportional to the square root of that number. So if you can reduce your energy spread by a factor of 4, you double the resolution. And so the hot field emitters, Schottky, are about 0.7 or 0.8 electron volt energy spread. The cold field emitters in principle can be a lot smaller, but in practice they're only slightly smaller. And then what that will do is it will give you an extra increment according to the square root of that reduction in the energy spread. And that of course is why many people have gone to 300 kV, and the company's gone to 300 kV, because if you have the same field emission energy spread, delta E over E at 300 kV compared to 100 kV, you get a factor of 3 fractional reduction, and that gives you root 3, 1.7 times better resolution. So whereas, let's say, a field emission gun at 100 kV, let's say it gives you 2 angstrom resolution, then the same electron source at 300 kV might give you 1.2 angstrom resolution, which is more or less where people have reached. And so you could imagine chromatic aberration, or monochromators taking you further forward. But most people in structural biology, this is my own personal view, don't really need or want to go beyond about 2 angstrom resolution. So the vast bulk of the data that people want to collect and structures you want to determine could be satisfied with a field emission gun at 100 kV. So it's a choice. If you're very, very interested in pushing the limits and going to high resolution, then obviously you need to do the very best in every area, otherwise you don't do it. And in material science now, obviously there are people going to 0.3, and there was even a 0.2 angstrom resolution structure that used aberration correctors and tychography on non-radiation sensitive samples. So in principle, you could imagine going forward. But most structures in biology, you get into multiple conformations, flexible structures once you get beyond about 2 angstrom resolution. So hopefully that's given an answer.
Thank you very much. So there's another question that is, it came from the YouTube about your Cryo-EM 1400 in dual microscope. So they asking, does it has a standard vacuum system and anti-contaminator, or was it modified to reduce the contamination effects? So there's a question about anti-contamination.
Yeah, so we've been thinking about moving in this direction for 4 or 5 years now, and we did hope that the companies would take the lead, and then all we would have to do is get money to buy one. But actually, because they didn't move in this direction, we decided that we needed to do a bit more work. So we actually did a lot of early investigation of the different platforms, Hitachi, JL, and Thermo Fisher, in terms of price and what the problems were. And based on that early work, we decided that the JL 1400 was a very good platform. And that's because it's very well developed. JL have sold 800 or 900 of these microscopes. So they can produce 100 a year. It's a very good, so we picked it. and measured ice contamination, and it's very good, although if you can make it slightly better, then you can go further. So we also asked JL, we said we would like the high resolution pole piece, which has a chromatic aberration of 1.8 millimeters, rather than the high contrast pole piece that most people buying the gels had been buying in the past, which has about 3 or 3.5 millimeters. So this is twice as good in terms of chromatic aberration, has a narrower pole gap, and they redesigned their anti-contaminator for the high resolution pole piece. And we are the only ones at the moment with that anti-contaminator, but it is a standard product from JL. So if anybody buys a JL 1400 with high resolution pole piece and the anti-contaminator, they will get the same, exactly the same microscope that I showed you in that image. But in the next year or so, we will be modifying it with a field emission gun. And at the moment we have a Dectris Singler detector, which is 1 megapixel only, but we need more bigger and faster detectors. So the future means improved detector and improved field emission gun on the top and bottom of the microscope. And possibly we may be able to make some slight improvements also in the ice contamination rate. But this microscope, we wouldn't be running it for 3 days for data collection. We'll only be running it, say, from 10 a.m. till 10 p.m. A 12-hour run, and then it would be warmed up every evening to do a cryocycling of the column, so to make sure there isn't any ice on any of the other parts near the specimen. So I think we're basically happy with it, but there will be 3 improvements: the specimen and the anti-contaminator, the gun, and the camera.
So basically everything.
Well, you're building on a system that's been very successful, and there's probably more 1400s in the world than any other microscope column.
Yes, you're right. But so you say you will improve also so you will install field emission gun instead of the current filament, right?
Yeah, I mean the problem.
Possible.
I mean there isn't. So what we're doing, there is actually no fundamental problem involving physics or anything. There's no fundamental problem to be overcome. For example, JL had a perfectly good 100 kV field emission gun in 1982 or 1983. So when I used to work on bacteria rhodopsin and went to Berkeley to work with Bob Glazer, Ken Downing, they had a JL 100B with a field emission gun. And it was very, very good. It was completely reliable. They never had to fix it. And so what's happened is, partly by pressure from the community, from us, the companies have responded to the request for better vacuums, for higher voltage, for more stable columns. And so now all the field emission guns that you can buy have been designed to work at higher voltage with SF6 to prevent corona discharges and so on. And as a result, they are more expensive. And so you cannot buy at the moment. There is no 100 kV, perhaps that's wrong. There may be 100 kV from Neon or from TechScan and so on. There may be lower voltage microscopes, but not for essentially the mass market of biologists, and also for less expensive platforms. So I think the field emission gun, the one we've focused on, is manufactured by a small company with about 15 employees in York in the UK. And this is Mohammed El Gamati, York Probe Sources. And they have been working for 10 or 20 years making field emission guns for SEM. And actually for many years they supplied field emission tips to the major companies, to JL, to Thermo Fisher and so on. And so they actually, they manufacture hundreds of these every year. 400, 500. So they're experts on field emission gun, but they had never worked above 30 or 40 kilovolts, which is SEM highest energy. So they have had to do a major investment to develop so it's exactly the same field emission assembly and source that they've been using for very many years, but it's now being repurposed to work on a 100 kV platform. And we're hoping it'll all end up being, it'll be quite expensive compared to tungsten, of course, but hopefully it will still keep the cost of the microscope within a reasonable bound. So you'll have to wait and see how much it costs the Tundra, and hopefully we'll hear that later in the meeting, and also how much once the gel and the field emission gun with a good detector are. But it'll be a lot less than the 300 kV state-of-the-art microscopes.
Yes, thank you. So speaking about detectors, there's another question from the audience. Are Gatan and FEI currently interested in developments of 100 kV detectors? And what are the most challenging aspects to overcome to optimize detectors for lower voltages?
Yeah. So I'll begin with just the most challenging things are that just in the same way that electrons interact with your specimen, the electrons interact with your detector. And so as you go from 300 kilovolts down to 100 kilovolts in the accelerating voltage, 3 times less energy, the tracks of the electrons in a silicon detector change from about 300 or 350 microns at high voltage down to perhaps 50 microns at 100 kV. And the way that the high voltage detectors have been made to work is by back thinning them, making a very thin layer of silicon, so maybe 30 microns in thickness. So the high voltage electrons go straight through. But the 100 kV electrons, if you put them onto a Falcon or a K2 or K3, they get scattered around, and the DQE and the MTF, the technical features of the detectors get worse and worse as you come down to 100 kV. And so by the time you're at 100 kV, you may as well have a phosphor fiber optic 30-year-old detector. So there are a number of solutions that you might adopt to make a good 100 kV detector. One would be to back thin it down to 5 or 6 microns. This is quite difficult to do. The thing that we've decided is easiest is to make the pixel bigger. So instead of having a say 6, 10, 14 micron pixel size, you go to 50 or 60 micron pixel size. And there are a number of companies now working on this, but the only one that you can buy at the moment is from that has a high DQE, comes from Detris or Medipix. They are detectors that were developed, hybrid pixel detectors for X-ray crystallography, and so they have thick phosphor and big pixels. And so the Detris one that we have now is a singler, and again we're the only people with a singler and on the microscope that I showed you, but Detris are able to supply them. So if anybody in the audience buys a JL 1400, they can buy a Detris detector to go on it immediately. But there are a couple of companies. One is the Rutherford Appleton Group with backing from the Rosalind Franklin Institute. They've embarked on developing a big pixels fast CMOS detector specifically for 100 kV, but that will be a year or two until it's available. And then I know that Thermo Fisher have also got an interest in developing a better detector as well, because we've been involved with them in trying to get a grant to do that work. And so I think all of the companies, once the detectors are available, they'll make them available as part of their platform. So the investment is underway, but at the moment it's still in early days for getting really good detectors.
Okay, thank you. So there's another question from the audience. Professor Henderson, thank you for the lecture. And did you expect such an intensive development of Cryo-EM in the early 80s? Was there a pivot point that changed your expectations?
I'm not sure I heard that exactly. Maybe you could repeat
Sorry,
it all.
yes. So did you expect such as intensive development of Cryo-EM back in the 80s?
Right. Well, obviously, until you actually solve all the problems, you don't know that it will work. But my own, let's say, scientific trajectory was that when I was a student, I worked on X-ray crystallography of enzymes, chymotrypsin, actually, which, interestingly enough, chymotrypsin is homologous to the coronavirus main protease. It's now a drug target, so it's similar. So, but then developed an interest in membrane proteins, and you have a session on membrane proteins in the meeting. And then we had difficulty making 3D crystals. Hartmut Mickel obviously was the first one to succeed really well. And so I switched with Nigel Unwin to doing electron diffraction. And originally I thought electron diffraction had the big power because you don't have to worry about imaging and all the electron optics. But round about 1980, after Jacques Dubochet had shown how to make these plunge-free specimens thin, and we tried all sorts of other ways of doing electron diffraction to get the phases of the diffraction spots from 2D crystals, we decided in our group in Cambridge that we needed to do electron imaging and Cryo-EM, cryo-electron microscopy. So we started doing that, but only on 2D crystals in 1984 or 1985. And then many of the problems that came up in the imaging, it was easier to solve them when you're working on 2D crystals because you have phases and you can compare them. And then it wasn't until 1995, really, that review that I wrote, that I mentioned, where it became clear that the real power of electron microscopy comes from not having crystals and then from doing single particles. So then we switched our efforts completely away from 2D crystals into single particles about 1995 or so. And then actually we thought then it would be relatively simple to do, but it turned out there were a lot more problems and you needed these better detectors and also much better software. So computers and the contributions, for example, of Georges Cherez with Relion, Nico Grigoriev with FreeAlign, and Steve Ludke on EMAN, and now the more recent ones, they've basically cemented the early hope that Cryo-EM would work by one by one addressing all the problems, so that now it's quite a powerful method. And if the right investments are made going forward, it'll become much bigger and much greater impact than even it is at the moment. So yes, I've always been optimistic, and actually this is a good piece of advice. If you're a scientist, it's always better to be optimistic than pessimistic. So.
Yes, you're absolutely right. So we actually almost at the time, so we have maybe time for one question. Again, we're going back to these detectors. So the question is, what would be magnification to have using Dectris detectors where the size of the sensor is about 50 microns?
Yeah. So Dectris is 75 microns, so we're using a magnification 400,000. So that means that the pixel size at, well, 400,000 is the nominal magnification. You get a bit more. So it's about, I think we think 1.1 angstrom pixel we get on that microscope that I showed you with a 400,000 magnification. But, you know, if you turn the knob, it goes up to 1.5 million. So we're not running out of microscope headroom on the magnification. And actually, we'd like, the Dectris is only 1,000 pixels square. We'd like 2,000 pixels square, which some people are working on, or slightly more in the future, we'd like 3,000 pixels square, which would be quite a big detector. But there's plenty of room. You move the detector further away from the microscope towards, but not below the floor.
Okay, yeah, thank you. So I think the last question about 100 kV microscope. Is it good for small proteins without any symmetry and with flexibility? So right now you show us only small proteins with high order of symmetry. So how about no symmetry at all?
Yes, so the constraints on what sort of molecule you can work at depends only on the size of the structure, not on the symmetry. It's just that if you're trying to show that the method works, it's much better to start with a high symmetry, because then you need, so for example, DPS has 12 subunits, so you need 12 times less particles to get to the same resolution. But there's nothing about the theory that says that single domain structures are any more difficult than high symmetry structures. And it's the same at high voltage or low voltage. And this advantage that you get from using 100 kV rather than 300 kV in terms of the information in the image for the same amount of radiation damage, I think it means that 100 kV microscopes out to a resolution of about 2 angstroms, they're going to be better than 300 kV microscopes for all specimens, but it'll be particularly good on small structures because you can make the specimen thinner. If your particle is only 60 angstroms in diameter, you can make a 100 angstrom thick specimen, and you get a much bigger proportion of the advantage in this elastic versus inelastic cross section. So yes, we are so this is, I should say, Chris Russo, his group, Greg McMullen, we think that 10 years from now, there will be more 100 kV cryo microscopes than there will be 300 kV. And they'll be being used both for screening and with a bit more effort on the software for high throughput data collection. So that the 100 kV, we think, is a big, big part of the future.
Yes, okay, great. Thank you so much. When I met first Dr. Nikolai Kiselov, who was working in Moscow in the Institute of Crystallography, he told me the same thing, maybe 10 years ago, that we need to go down with the KVs because we will get better contrast and better data. So yeah, I think it's a great future of the electron microscopy. So now there's a time. Is this end of this lecture and end of this question. So thank you very much, Richard, for very great lecture. And now we need to go to the next speaker. So we are looking forward for you to coming in Moscow in the near future. So you are very welcome. We would be waiting for your visit. So bye-bye, see you. Bye. Okay, dear colleagues, our next speaker is Professor Gunnar Schroeder from Institute of Biological Information Processing in Jülich. So his group determines the structure of amyloid fibrils, and as all of you, I think, know, amyloid fibrils are very bad. They are related to a lot of different molecular diseases like Alzheimer disease, Parkinson disease, diabetes. And Professor Schroeder was giving a talk 2 years ago on our second conference. So now we will wait for his very interesting lecture. So please.
Yes, thank you very much for the kind introduction. And I'd like to thank all the organizers for giving me the chance to present our work here. And it's really too bad we cannot be in Moscow. I was there, as you said, 2 years ago. It was a fantastic meeting. I had a great time, and I really hope to come back at some point. So since this is a kind of a methods technology session, I thought I will also speak a little bit about our computational method developments. But I will do this in the second part of my talk. So I start talking about amyloid fibril structures, and this is a topic that has been quite dominant in my group for the last couple of years. So first, I want to say a few words about amyloids. I mean, in your introduction, you already said amyloids are a problem in several diseases. So several neurodegenerative diseases like Alzheimer's and Parkinson's and so on. You will find amyloid deposits in the brain of the patients, but there are other amyloidosis where you find these deposits in other parts of your organs. But there are also functional amyloids, and there's even actually a large number of functional amyloids. So it's not only disease related, it also can have actual function. And so amyloids, you typically talk about this, the amyloid state as this fibrillar state where you have your protein or peptide arranged in a flat planar-like way, and these sheets, they just stack up and form this cross beta pattern where you have hydrogen bonds, like beta sheet hydrogen bond pattern all along the fibril axis, like is shown here. I hope you can see my pointer. So you get this helical fibril arrangements. This is a typical amyloid fibril structure, and the difference, the distance between these sheets is like this 4.7, around 4.7 angstrom in this sheet. And because all these amyloids, they basically have that same architecture, this layered cross beta pattern, the most interesting thing and the main feature that sets them apart from each other is the cross section. So we typically mostly look at the cross section because that tells you how the fold of this amyloid fibril looks like. So in principle, you can think of this as a 2D folding problem in contrast to the 3-dimensional folding of your regular globular proteins that we normally speak about. Amyloids, because along the fibril axis, they all look pretty much the same. It's mostly a 2-dimensional folding problem. So because the general architecture is always the same, so you have backbone hydrogen bonding that defines this amyloid fold. In principle, there's no reason any protein could go into such an amyloid state. Of course, there are some proteins or peptides that are more amyloidogenic, that have a higher propensity of forming these fibrils, but in principle, you can stretch out any protein basically, and you form a pretty energetically favorable arrangement by just forming all these hydrogen bonds. And in fact, there's one structure that we have looked at, the SH3 fibril, that is not really functional or not even disease relevant. It's not relevant for any disease or function. It has been studied as a model system for amyloid aggregation. So the SH3 domain is usually found in kinases. It has this shows here the native fold. It's a small domain, but if you take out this domain and you just put it into low pH, it starts forming these very nice fibrils. And if we look at in general the folding landscape of amyloids, let's start here with the monomers. So you have the monomeric peptide or protein, then the natural route or towards the native fold would go like this. Even though most of the amyloidogenic peptides and proteins are actually disordered or intrinsically disordered proteins, IDPs, at least they have large parts of in their sequence that are not ordered. And the route towards the amyloid fibril states goes down here. So you have some monomers assemble and they form some seeds, some fibrillar oligomers, from which more monomers are recruited and add to these seeds, and they grow into long fibrils. And then these fibrils can then further become the non-soluble part and end up in these deposits. For example, the plaques that you find in the brains of Alzheimer's patients. But such kind of deposits you can find depending on the disease or the function, and in all other places in different organs. Another mechanism that I would like to mention here, starting from these smaller seeds or oligomers, you can also have cross-seeding. That means you can form seeds from one type of protein, and just due to some structural similarity, another type of amyloidogenic protein can start to assemble on the seed and grow into a different types of, or maybe slightly different type of fibril. So you can have that's referred to as cross-seeding, when one species of an amyloid protein seeds a different amyloidogenic protein. And also you can have secondary nucleation. That's an important process in the growth of fibrils and in the proliferation of amyloids. Once you have formed fibrils, this most likely the surface acts as a catalyst for new aggregation of smaller oligomers, and then also further growth into more fibrils. And then there's another route that would be referred to as the off pathway, because it's not on pathway to the fibrils, but kind of an alternative aggregation route that also results in some smaller oligomers at first, and then you get further growth into these curvilinear fibrils, which we observe more as kind of curvy, not very high symmetric aggregates that look much more disordered, and they don't have this characteristic 4.7 angstrom beta sheet pattern, so they are probably just much more disordered. And I should mention that these smaller oligomers are the kind of, at the moment, the main targets for several neurodegenerative diseases. They seem to be most toxic, and it also seems like that probably these off-pathway oligomers are maybe even more toxic than the on-pathway oligomers. But the structures of all these smaller aggregates are not known at all, so we have no idea really how they look like. And also these curvilinear fibrils are very difficult to analyze because of this low order in general. Okay, I want to tell you first the story of one amyloid fibril that we have looked at more recently, and that's the Eyelid Amyloid polypeptide, IAPP, or also sometimes called amylin. Is a small hormone peptide, 37 amino acid, has like these post-translational modifications. There's a cysteine, a disulfide bridge here, and the C terminus is amidated. The IAPP is produced in beta cells of the pancreas. It's co-secreted with insulin, and it's responsible also for controlling blood glucose levels together with insulin. And this small peptide is highly amyloidogenic, so it readily forms amyloid fibrils, and it's strongly coupled to type 2 diabetes. So in diabetes patients, you often see these deposits in the beta cells of the pancreas, and that consists mostly of IAPP. So we did Cryo-EM on these IAPP fibrils. So those are in vitro preparations, and you immediately see 3 different polymorphs. So those are just different types of fibril structures. You see they have a different width, they have a different helical twist. So the crossover length here between the filament, between the distance between these crossovers and the helical filaments are apparently quite different. So we So we have to, so we pick them separately and then reconstructed each of these polymorphs separately. The third polymorph is really very weakly populated, so we only have about 1% of all the fibrils are this this specific type of polymorph. So we get only very low resolution. We cannot really say much about that one. But the first two polymorphs reconstruct to a reasonable resolution. And, we can start building atomic models, and we'll just basically just talk about the first polymorph here. And that is looks like this. So again, we basically only look at the cross section of the fibril here. Contains two protofilaments, so two chains of amino acids that are that form this fibril, and it has been known for a long time that the central motif here, that's called the NNF Gale motif, that's very important for the aggregation. So these, if you start mutating these residues here, then you lose the ability to form these fibrils quite quickly. So interestingly, this motif is really at the core of our fibril, so that makes sense. And interestingly, there's also a drug that has been developed that's an analog of IAPP that's called Premnentite, or is I think the brand name is Simlin. And the idea was to mutate some residues from red IAPP, because it's known that red IAPP is much less amyloidogenic, so it doesn't form as easily fibrils. It still forms some fibrils and it still aggregates, but not as quickly as the human sequence. So they mutated 3 prolines here into the human sequence, and they give that to patients that have to kind of support the functional role of IAPP. Give this as a supplement of IAPP, but with the big advantage that it doesn't easily aggregate. So if you just give regular IAPP, it would immediately aggregate, and it's very difficult to actually give this to patients, to diabetes patients. So with the help of this structure, we might be able to come up with a better drug with a better IAPP analog that is even less amyloidogenic and maybe has better function than this modified IAPP analog. So another interesting point about IAPP is that there's a link between diabetes and Alzheimer's disease. And we have been interested in Alzheimer's disease for quite a while, and now it was interesting to work on some fibrils that are linked to diabetes. Diabetes patients have about a 2-fold higher risk of developing Alzheimer's disease. And IAPP and A-beta both co-localize both in the pancreas, in the eyelid amyloids of diabetes patients, but also in the brain deposits, in the plaques of Alzheimer's disease patients. So there is clearly some link, and it's also been shown that there's a cross-seeding between IAPP and A-beta. And I just told you before that what cross-seeding means. So you have the existence of seeds of one type of protein can accelerate the growth of fibrils of another species. And this has been observed also in transgenic mice. So there's a molecular link as well between IAPP and A-beta. The sequence alignment gives you some similarity. You find a similar kind of NNF Gale motif in IAPP. You find something that's somewhat similar also in A-beta, but it's in overall not a super strong homology here in the sequence. A few years ago, we solved the structure of an A-beta 42 fibril, and it shows here this, again, it contains 2 protofilaments, and it contains this typical LS fold. So here we have this S shape, and then the L and the N terminus. And now if we are comparing our IAPP structure with this A-beta structure, we see that this actually overlaps quite well. And this S shape is very similar. So you can imagine that maybe that similarity, structural similarity, is sufficient to seed the growth of A-beta fibrils here. Of course, this is just a rough comparison. There's no structural picture yet. We haven't really solved the structure where we see the connection between these fibrils. And interestingly, even if you arrange them in an anti-parallel way, they fit even slightly better. So it's not clear exactly how that interaction works, but just based on the similarity, we think it's an interesting. It's an interesting point. It could be actually the mechanism how this cross-seeding works. So a fundamental property of amyloids in general is the ability to replicate, and that's described by the prion concept. So you have seeds, you add monomers, and that gives you a growth of fibrils. And there's a common experimental technique that's called PMCA that's used to amplify prions in general, amyloid fibrils, for example. Usually with the goal of increasing the sensitivity of detecting small amounts of these prions. And an important question is how well these amplified structures actually resemble the seeds, or whether they actually replicate the structure, which is usually what people have in mind, I think. And there was a very interesting work from the Scheres and Gödert groups last year and also this year. So in the first paper, they looked at alpha-synuclein fibrils from patients with multiple systems atrophy. That's also a disorder where alpha-synuclein aggregates. So they extracted fibrils directly from the brains of these patients, and from several patients actually, and this is the first line here. They show these different structures, which shows the structure of these fibrils in the brains of these patients. And then in the second work, they used these structures here as a seed for amplifying fibrils. So they added monomers, recombinant protein, to these seeds here, and this is what they observed. So they actually recover a similar fold only in one case, but in other cases they get relatively different structures. So they question basically with this work whether you really reproduce or replicate exactly the seed structure. And we did recently similar experiments. We used the brains of MSA patients to also amplify structures. And we also use the brains of Parkinson's disease patients to do the same thing. And what we find is are these structures. So we solved the fibril structures, and this is the polymorph we get from MSA amplified fibrils, and this is the polymorph we get from PD amplified fibrils. And for comparison, again, this is what I just showed you. This looks very similar to, it's almost the same fold as the ones that Scheres and Gödert showed from their amplified MSA structures. And actually, this is very similar to, basically identical to the polymorph 2A and 2B that Henning-Stahlberg's group published first in 2019 here. So this is basically the same structures. So I wanted to compare this a bit closer because at first it looks like these structures here have not much in common with the seeding material. But if you turn around like our fibril structure and our work, which is also similar to the Scheres-Gödert amplified and also the Henning-Stahlberg polymorph, if you turn them around and arrange them in an anti-parallel way, you get back a relatively well alignment, quite well aligned. Of course, that means that the sequence don't match. It's a completely different sequence that's on top of each other, but just the template of the backbone is very similar. So you can easily imagine that this is the actual seed region, and it comprises about 40 amino acids. So it's a rather long stretch of structural similarity that might be enough for seeding these fibers. But then in the end, what the exact structure that you get that probably also depends not only on the seeding on the seeding template, but also on the environment conditions like pH, buffers, salts, and whatever. So amplification does not necessarily reproduce exactly the seed structure. The seeding itself probably just needs some form of common core, but it doesn't have to be in a parallel in-register arrangement, but it just probably just need to have a certain template that fits with an energetically favorable arrangement of the new polymorph that is growing there. But still, the amplification seems strain specific, so we get almost exclusively this polymorph from our MSA amplified, and almost exclusively this polymorph from our PD brains. And also they have different properties, which I'm not showing here, but we have they behave differently in cell assay experiments. So they clearly have different properties, even though their protofilaments are pretty much the same. Their interface is different. Okay. In the last few slides, I want to talk a bit about computational method development, and I usually start by pointing out that there's a difference between what we refer to as density variance and conformational variance. So if you think about such an elongated structure here, maybe a helix or something that is elongated, if you move this structure here by some amount along the long axis of the structure, you produce mostly density variance at the tips of this elongated structure, and no variance of density at the sides here. But if you make the same amount of movement, so let's say you move it 5 angstrom this direction or 5 angstrom this direction, you produce density variance all along the structure here. So it seems like if you just look at density variance, you would think this motion here is larger because it produces much more density variance than this motion, when in fact the motion would be exactly the same. So in particular, domain rotations, for example, they can easily be underestimated when we have maybe a domain that is rotating but also translating a little bit. Then the translation would produce much more density variance than the rotation. So you would think the rotation is not as dominant as the translation. So all the standard image classification methods, they look at density variance. You sort images based on density similarity, how similar they appear on the image. But I think if you want to optimally resolve different conformational states, or you also want to optimally improve the resolution, you should be looking for conformational similarity and not for density similarity. That can be very similar, but it can also be quite different, and it's definitely not the same. So I have another picture just to explain this. So I have two panels here which basically describe the same thing. This is the motion of some density blob by a certain amount. And you can, in density space, you describe this by density at this voxel goes down and density at this voxel goes up. If you describe the whole thing in conformational space or in Cartesian space, you would say this point here moves in this direction and this point moves in this direction. So it's just a different space in which you're describing the same motion. And we are trying to develop methods that work in conformational space and not really in density space. So one technique that we're working on is to elastically align density maps, and this is work that's has been done by Amura in her PhD work a couple of years ago in my group. So let's
sorry,
say
Gunnar, you only have 3 minutes left.
Yes, I know. I'm almost there. So we're describing so we're fitting one density map to another density map, and we are describing the map as a flexible body by just throwing in point masses and springs, and we are using our program directs for structural refinement to the fitting. This is general enough to work with general point masses and springs. And this video shows the underlying deformation of the grid, and this shows this video shows the same trajectory, but it's just the isosurface representation. And when you do this, you can take, for example, subtomogram averages or different classes from single particle reconstructions to align them elastically, average them, and then improve the resolution. So that was basically all I wanted to show. Those are my acknowledgements, and then I'm done. Thank you.
Well, thank you very much for a very interesting talk. So may I ask you a question? First of all, this DIREX program, I mean, it's your own program, internal program, or everyone can use it? Is it available somewhere?
Yes, it is available. If you go to our group website, my lab website, then you find a link. It's open source. You find it you find the link. It's easiest to go through our lab website, and you find it there.
So there's one question from the YouTube. How do you determine twist angle to perform the helical reconstruction of the new structure? Is it possible to determine the twist angle from the cryo dataset without any prior knowledge? Yeah,
I mean, the first idea of the helical twist symmetry parameter you get directly by looking at the micrographs, because if you have the crossover length, you know what that corresponds to 180-degree rotation of the fibril, and since we know the rise is basically always 4.7 angstrom or slight variations of that, you have a first idea of the twist already directly from looking at the raw micrographs. And that's what we usually use to start our reconstructions with, and then the helical symmetry parameters are optimized later during later rounds of density refinement.
Okay, thank you. So I think we can ask last question. In the protein folding and misfolding slide, you mentioned difference between oligomers and fibril oligomers. So how we distinguish between them?
Yeah, it's just it's not clear how they structurally look like. It's just basically just a model how to think of these different aggregates, and there is clearly in a pathway from monomer to fibrils, and that must involve some seeds on which the fibrils can grow. But we also observe like these curvilinear fibrils, which are clearly not very well ordered, and which I don't know what this is, whether they are aggregated smaller oligomers or whether they have a different type of structure. We don't know really, because it's very hard to reconstruct anything there because they're not very ordered. But there are also oligomers that do not go on further for fibrillization. So I don't know what their structure look like, but I assume that the ones that go on pathway towards fibrils, they probably have some fibril similarity already in them. That's why I call them fibrillar oligomers. But structurally, I cannot really say much.
Yes, okay, thank you. And I just have very, very last small question. Maybe it's, so because you're doing the reconstruction of amyloid fibrils, they're pretty long. And when you have them frozen, they are parallel to the surface of the eyes, right? So are they not damaged by this ice-air interface?
Yeah, you see that, and in some preparations, you see, for example, very straight filaments. They're not twisted anymore, and I think this is probably mostly an artifact from the air-water interface. They start sitting at the air-water interface. They detwist basically, and you see straight filaments, and those you cannot really work with because they don't have a helical symmetry, and then you just get one view of these fibrils, and that happens. I mean, in one of the data sets, actually, we had a large fraction of fibrils that are not twisted and are probably just sitting at the air-water interface. But that's a tricky balance that you have to find between. You want to have thin ice, of course, but the thinner the ice, the more artifacts you get from the air-water interface.
Okay, thank you. So now I think we have no time for questions now. So thank you again, Gunnar, for very interesting talk, and we're looking forward for next meeting.
Yes.
Hopefully, yeah, with
You
a
too.
better epidemic situation. Thank you. Bye.
Thank you. Bye-bye. Thanks.
Hello again. So the first day of our conference is dedicated to advances in electron microscopy technology and processing. So right now we already heard about advances in field emission guns and detectors, about helical reconstructions, and now we'll be introduced to Cryo-EM tomography. And our next speaker is Dr. Dmitry Tigunov from Max Planck Institute of Biophysics. You're welcome.
Well, thank you very much for the introduction and for inviting me to your conference. Just a small correction for the credentials. I'm, in fact, at the Max Planck Institute for Biophysical Chemistry, not the one in Frankfurt.
Oh, sorry.
So I think like everyone else, I'm quite heartbroken that I cannot join you in Moscow for the party. I think the last time I was in Moscow was maybe around 1993. And back then, no one invited me to a party because I was only 5 years old. Well, maybe better luck next time. Anyway, tomography. So tomography is great for looking into cells because they are so crowded, and tomograms allow us to resolve them in almost 3 dimensions, not counting the missing wedge. But if we try to do the same kind of single particle analysis that we like to do with in vitro data and micrographs, using a state-of-the-art single particle-like pipeline just a few years ago resulted in rather limited resolution for the subtomogram average. Here it is shown for a very good data set and a state-of-the-art pipeline using warp and Relion. And the best resolution we can get from this was 11 angstrom. Now, as we already saw in Richard's talk, the resolution, especially for ribosomes that we can expect for conventional data, is much higher. So why does the subtomogram average not look like this? Normally, when we acquire a tomographic tilt series, we expect it to look like this. So we put the sample into the microscope, and then we tilt the stage, and at every consecutive tilt angle, we acquire an image. Now, in reality, unfortunately, the tilt series looks more like this. And this is because as we irradiate the sample with electrons, just like with conventional micrograph data, there is beam-induced motion, which leads to the sample changing. And if we look at the individual tilt images in this tilt series, we can see that in each individual image, there is beam-induced motion-related blurring. And we can use the same kind of algorithm that we use for aligning conventional micrograph movies to get rid of this intra-tilt image movement. But then we're still left with this large-scale beam-induced motion across the entire tilt series. And this is essentially what limits the resolution. Now, in the movie industry, if we want to track the motion of actors, we just strap fiducial markers to them. And in fact, the very same thing is being done conventionally in cryo-electron tomography, where even the very, very first time anyone attempted to do electron tomography, and that was Roger Hart back in 1968, even then, he already came up with the idea of adding gold fiducials to the sample, because gold provides very high amplitude contrast in TEM images, and so you can somewhat accurately track those gold fiducials. Now, of course, in 1968, this technique was still a few decades away from its prime time, just because the technological stack was not there at all. But even today, we are still using gold fiducials to be able to perform this initial tilt series alignment. But because the gold fiducials are quite different in their shape, at least at high resolution, they're quite different, we cannot track them very accurately. And for some samples, like in situ cell lamellas, we cannot add gold fiducials at all. Now, luckily, our cells contain lots and lots of natural fiducial markers, and that is the proteins themselves. And if we have high resolution structures for some of these proteins at least, we can track them with very, very high accuracy, or at least much more accurately than gold fiducials. And this idea is not exactly new, but I made a new implementation for another take on this idea and called the whole thing multi-particle refinement. So in conventional single particle analysis, we treat each single particle, as the name implies, as in fact a physically completely isolated single particle. And we align the pose of each particle completely in isolation from all the particles that are in fact physically within the very same ice layer. Now, in this multi-particle refinement that I implemented, we treat the contents of the entire field of view, so of an entire micrograph or an entire tomogram, as a multi-particle system. And we do not only optimize the individual poses of the particles, but at the very same time, we also try to fit another set of hyperparameters describing the changes that this multi-particle system undergoes. And these are the types of changes that this new algorithm can fit. Now, the global movement and rotation are quite straightforward. This is both because of the mechanical instability of the microscope stage, as well as large-scale beam-induced motion. You cannot really disentangle them, but luckily we can fit all of them simultaneously. And then we have more nonlinear kind of image space and volume space warping, and this is then caused by the beam-induced motion as a function of the exposure. And especially for thick samples such as cell lamella, this volume space warping, which can basically describe a kind of shearing that individual sample slices undergo relatively to each other, there it is quite useful. And for very thin in vitro samples, we also have this doming, which was described already quite a while ago. And that some of the motion correction programs, such as, for example, Motion Core 2, also take advantage of as an additional prior. And so this is the pipeline that I ended up implementing. Data comes in from the microscope, and then it is pre-processed by another package that I published earlier called Warp. And Warp does all kinds of motion correction, CTF estimation, particle picking for tilt series, also tilt series alignment through IMOD. It reconstructs the tomograms. And once it has all of these pre-processing metadata, it can export the picked 2D or 3D particles into another piece of software that we already heard about a lot today. That is Relion. And Relion has lots and lots of different algorithms for working with such data. We can classify them in 2D or 3D. And we can also obtain more accurate global pose alignments in 3D in Relion. And then we take all of these global alignments and we import them into a new tool called M. And M then performs this new multi-particle refinement, where it optimizes both the previously or the pre-refined particle poses, as well as a relatively large set of hyperparameters describing the deformation that the sample undergoes in each field of view. And then, if you're already happy with the result, this will be the final map. Or you can take those fitted hyperparameters for the beam-induced motion and go back into warp. And this is especially useful for in situ samples where with the initial alignment you can quite well work with huge macromolecules like ribosomes and then use them to improve this multi-particle alignment. But then you can take the improved alignments and now you're hopefully able to work with smaller molecules which previously just had too little signal to align on at all. But now with the improved alignments, this hopefully works better. And you can do another loop in this pipeline, going back to warp, re-extracting some smaller molecules, then back to line and back to M. And then hopefully you have much nicer maps for those smaller molecules. And the very first thing that we tested when M was finished was how well did it do with conventional micrograph data, because micrographs are really, I mean, conceptually just a very special case of tilt series where you have only one tilt angle, right? But you have still multiple frames. And so we took this super high resolution epiferritin dataset. At that point, it was still the highest resolution dataset available on Empire, acquired on a gel microscope with a cold field emission gun. And for this dataset, Takanori from Shore's group had already produced an extremely impressive result with 1.54 angstrom resolution. And using M, we were able to improve this to 1.34 angstrom. And some of the technical improvements here were, for example, the inclusion of Ewald sphere curvature, both in the particle post refinement as well as the CDF refinement. Previously, in Reliant, you can only use Ewald sphere correction for the reconstruction, and in Freeline, you could use it also for the particle alignment, but one new thing that we added here was that was also used in the CTF refinement. And this was probably the major reason we were able to push it to even higher resolution. And another very interesting thing that we were able to look at with this data set is this doming that I already mentioned before. Basically, M can fit the defocus change for the entire field of view and even resolve it spatially as a function of the accumulated exposure. And in fact, we do see a rather drastic change, or at least an apparent change in defocus during the first couple of frames in those movies. And we then also benchmarked the whole pipeline on previously processed and published data sets for tomograms. And in all cases, this new pipeline did a little bit or a lot better than the competitors, those being EMAN and EM Clarity, also implementing a take on a similar idea for multi-protocol refinement. And since both parts of the pipeline did quite well, we were really curious whether now there was still any difference in resolution if we took the very same sample, the same amount of data, and acquired one half of the data set as conventional movies, or as I call them here, frame series, and the other half as tilt series. And we were, together with Christian Dienemann, who's our facility manager, very excited to find that using this multi-particle refinement, there is now, at least for ideal samples, absolutely no gap in the resolution achievable. Previously, you may remember that subtomogram averaging was always this kind of lowish resolution method. But now, given the very same sample and the very same microscope conditions, we can bring both types of data to the very same resolution. Of course, we usually use tomograms to look at much more difficult samples than what we would usually look at in vitro. So the resolution in the end will still be quite a bit lower, but at least we know that we do not lose any resolution by simply using tilt series. But the most exciting result here was, of course, for an in situ sample. And this came from a collaboration with Julia Mohammed and Liang at the EMBL in Heidelberg. And there, Liang acquired a set of tomograms of a very small bacterium, Mycoplasma pneumonia. And this bacterium is in fact so small that we do not have to fib mill it to make it thinner. It is already thin enough just by squeezing it in a film of water on a grid to be able to image it at quite high resolution with a TEM. But of course, it's still an actual in situ sample. It has all the complexity, all the crowding, has all this beautiful chaos that apparently is life. We were extremely surprised when, after we reached a resolution of about 11 angstrom using the old warp and reliant pipeline, the resolution just kept getting higher and higher with each iteration of refinement in M, and finally reaching almost the Nyquist limit for the data, which was 3.4 angstrom, and we did in fact reach 3.5 angstrom here. And this is just to show you that the resulting map does in fact have all the bells and whistles you would expect at this 3.5 angstrom resolution. And perhaps the most exciting thing here was that those bacteria were treated with an antibiotic, chloramphenicol, to stall them, because this was actually just a control data set for a whole different kind of experiment. No one expected to get anything exciting out of these data initially. But they had this antibiotic inside, and in fact, when we fitted a structure from E. coli with the antibiotic that was previously solved, we did find the antibiotic exactly where we expected it to be from the E. coli structure. And in a previously published map of the non-stalled ribosomes, this density was definitely absent. Now, it is quite tempting to think here that we were only able to reach this very high resolution because the ribosomes were stalled with the antibiotic. But this 5.6 angstrom map is actually from a whole different paper from essentially a still not fully developed alpha version of this pipeline. And in the end, using the very same pipeline, our collaborators were able to push the non-stalled ribosomes to, I think, something like 3.8 angstrom, so almost the same high resolution. But of course, there is still a lot more flexibility in those non-stalled ribosomes. For the last few minutes, I just wanted to give you a very speculative prediction for what I think we will be doing with in situ samples in the future. Right now, when we perform any kind of particle averaging in 3D, we are essentially denoising them by finding a model that explains as much of the experimental data as possible, giving a certain forward imaging model added to it. And at the same time, deep learning with convolutional neural networks had been showing extremely impressive results for just single image denoising. But to train such models, until very recently, you always needed to have some kind of noise-free ground truth. And we just don't have any kind of noise-free ground truth in Cryo-EM, right? So I was extremely excited when I first saw this paper from NVIDIA about an algorithm that allows you to train such denoiser models without any clean data at all. Instead, it only requires 2 independently noisy observations of the same signal. And in Cryo-EM, we have lots and lots of such pairs of independently noisy observations of the very same thing. And the most interesting one here is for tomograms, we can reconstruct 2 tomograms using either all odd and all even tilt images independently, or we can take all odd and all even frames in each single tilt movie and then reconstruct a pair of tomograms based on that. And then because the model just doesn't have nearly enough learning capacity to learn this completely random noise pattern in all of the data, instead, quite amazingly, it learns to denoise the data. And this works for all kinds of data in Cryo-EM, for conventional 2D micrographs, where it helps you a lot with just validating your particle picking results. It works very well for reconstruction denoising for single particle maps. In fact, M uses it to regularize its maps based on local resolution, even though this entire denoiser does not have any kind of concept of resolution. It doesn't know what an FSC curve is. It doesn't have arguments with Marin over the right threshold to use as a cutoff for this FSC curve. Instead, it only looks at a set of 2 independently noisy half maps and then learns to filter them. But the most exciting application here, I think, is for in situ tomography, where for this very high resolution data set that I already showed before with Mycoplasma pneumonia, those tomograms were acquired at very low defocus. So you cannot actually see much at all in the raw tomograms. But if you train a denoiser based on these data, you can see so much more. And here is just a larger version of the same tomogram. I think we can all agree that on the left it is hard to make out any kind of details, whereas on the right you can see all the beautiful complexity that you would expect in situ. And I think in the future, such denoisers will become much less naive than the very first iteration of the algorithm that we're currently still using. And if even now with this primitive algorithm, if we have some very frequently recurring structures in the sample, for example, if we try to denoise a tomogram of an in vitro apoferritin sample that is just covered with the very same apoferritin molecules, the model would already learn a much higher resolution prior for those recurring molecules. And I think in the future, if we manage to figure out how to first make such denoisers more rotationally invariant, because current implementations using CNNs are still not rotationally invariant at all, but also to store and also successfully retrieve some structural motifs that are recurring in the data, I think we will be able to get a much more interesting picture of such in situ samples than if we were to try to solve them, essentially what we're doing now, particle by particle, because a lot of the things in there are just not really particles at all, but still they have some recurrent structural motifs that such a deep and powerful denoiser model, hopefully in the future, will be able to learn. And with this, I would like to thank my boss, Patrick Kramer, without whom none of this would have been possible. He's been very supportive over the years. Christian Dienemann is our facility manager, who acquired these fantastic apoferritin data. Julia and Liang from the EMBL in Heidelberg provided those mind-blowing tomographs of mycoplasma pneumonia. And if you would like to use or at least try any of the tools that I mentioned in this talk, you can find all of them open source on GitHub or already precompiled as binaries on the website. And if you would like to follow the latest developments, then please follow me on Twitter. And I think we still have time for a few questions. So thank you very much.
Yes, thank you, Dmitry. Very nice talk, and actually it's quite amazing because even I remember about 20 years ago at the conferences, people were discussing the resolution about 50 nanometers or that electron tomography can reach. And now you getting very high resolution, which is comparable to the single particle and probably even better. So this is a great advantage. I probably have a question about, so just whatever, hour ago, Richard talked that, answered to the question, and he said that the resolution depends basically on the number of particles, right? But when you're doing the TIL series, then it's limited by the number of TILs. You cannot increase, right, the number of TILs. So does it affect your resolution in tomography or not?
So first of all, you can and you probably should in the future try to increase the number of individual tilts in this tilt series by basically fractionating the dose much finer between the individual tilts. But of course, we still have to find out whether this actually provides any benefits. But my feeling is it would provide some benefits just from a purely information theoretical point of view. The number of particles in each field of view is quite critical for this kind of multi-particle refinement because you try to use as much signal for this hyperparameter fitting as possible. And I think there is also a very interesting discussion to be had for in situ samples. As we already heard before during this conference, sample denaturation at the air-water interface is quite limiting for many samples. And I think even for seemingly very good samples, some of the molecules are still stuck at the air-water interface. Whereas for these in situ samples, we have no such thing at all. So I am wondering whether part of this relatively high resolution and a very low B factor was because those ribosome molecules were in perfectly pristine condition and the angular distribution was perfectly uniform compared to conventional in vitro samples.
Okay, thank you. So there's another question from YouTube. Have you tried to apply M to membrane proteins? Is lipid bilayer signal a big problem?
We did test it with some membrane proteins, and the bilayer signal was not any more of a problem than it is for conventional refinement.
Another question from YouTube. What do you think would be the limit of a molecular size in 150 nanometers thick sample to get to high resolution?
Yes, that is the best question. And I'm sorry, I kind of avoided this discussion in my talk. Ribosomes are absolutely special in many of their properties. They're huge. There are so many of them. And this is certainly one of the reasons it works so well even in thick samples. But we cannot really decrease the sample thickness, at least not much lower than 100 nanometers, if we want to still have any reasonable amount of sample left for analysis. So far, I think the lowest we've managed to go was maybe around 800 kilodalton for any kind of high resolution. But this is not because smaller things didn't work out at all for refinement, but rather because those small things are increasingly harder to find in situ and in thick samples in general. And I think this is still probably the biggest unsolved problem for the analysis of in situ samples, just being able to find your molecule of interest in there, because none of the currently available approaches work well for that. So I think once we can identify smaller things more robustly, we will see this size limit also go down for what can be refined to high resolution in situ.
Okay, thank you. So we don't have time to more questions. So thank you again, Dmitry, for coming here virtually. And thank you. See you hopefully next time in person. It would be probably nice experience to you to visit modern Moscow.
Yes.
Comparing to 1993.
Yes, it's a very different city now, I think. Looking forward to that. Thank you.
Thank you. Bye. So the last speaker before the break will be Michael Holmes. So he's staff research scientist at European Synchrotron Radiation Facility and EMBL. And he will tell us about the situation with electron microscope in Grenoble, France, and also about his own data. So actually, I think it's a good idea to, if you start with this very cheap, not very cheap, but cheaper microscope to check your samples. After that, you can go to the higher research facilities like these in ECRF in Grenoble or something similar to get much better data. So yes, please, Michael.
Thanks a lot for this kind introduction, and I'm really happy to speak here today among all these wonderful talks we saw already. So yeah, indeed, I'm based now in Grenoble, and I will speak about partly of my talk about the facility setup we have here in both institutes, and then I will talk also about my own research. So first, a short CV of mine. I started actually not in Cryo-EM, but I was working in, sorry, I think I need to restart sharing my, I'm very sorry for that.
Okay, we can see your presentation.
I'm sorry. I'm very sorry. Okay, so I started in actually in the Aptamers field, and after that, curiosity brought me into Holger Stark's lab in Göttingen. Sorry for this short interruption. So I joined after working in the Aptamer field, Holger Stark's lab in Göttingen. And this was in 2011. At that time, they had only one Cryos microscope. And then I stayed for a postdoc stay there before moving to Grenoble. And basically here, I'm helping to building up the Cryo-EM facility since 2017. And yeah, so in Grenoble, we have, when I arrived, there were many projects full of potential, and mostly because there's a very strong crystallographic background here in Grenoble, but not yet the sufficient infrastructure. And that changed in the upcoming months and years, and accumulated in the installation first of the Cryos G3, and later on one glaciers in EMBL and also one glaciers at IBS. So, and soon we are actually going to have another high-end microscope to arrive on campus. So on this EPN campus, which you see here, we have 4 institutes doing structural biology, and 3 of them having their own Cryo-EM infrastructure. And I play actually a dual role, one within EMBL and one within ESF. And I will start with ESF, and what you see here is actually the ESF team guided by Christoph and Isai. And basically, there are 4 scientists involved in running the cryos and doing user experiments, which is Isai from ESF, Greg from IBS, Dauda from ILL, and me from EMBL. And the original setup, which we used for the at the microscope, is shown here on the left. But since then, a lot has happened actually, and which mostly is about software upgrades, camera upgrades. Currently, we're having the K3 upgrade, which actually is happening really now, and also about our data storing and image processing pipeline. So now what we do in ESF is actually that we use Scipion and we go over pre-processing to picking and to declassification within experimental time. And what we offer to users is actually, for external users, is only single particle experiments. There are 2 different application schemes to apply, which is either you are in a block allocation group or not. And we expect pre-characterized samples. This can be or should be pre-characterized by 2D classification and a microwave overview image. And over the 3.5 years we are running the platform, we have achieved many publications. There were 90 publications, for example, in 2020, and you see, for example, NSP1 protein from chikungunya virus, or different states of influenza virus, RNA polymerase, the photosystem 1, or serotonin. Most users which we have come from France, Spain, Israel, Italy, or UK, but you see here in the plot all the other countries. And we had already quite some upgrades, and you see especially that over the time when we started, we created much more data, and especially with fast acquisition from the microscope, we needed to compress data, and now in 2021 probably this will happen again. And now I want to come to a new project actually, which is, I talked about pre-characterized samples. Not every lab in the world has yet the possibility to perform pre or cryo-EM experiments. So that's why we wanted to offer like a freezing and screening collaboration using actually the IBS glacius microscope, and pipeline this then into CMC01 when the project is successful. For that, we only expect pre-characterization biochemically for homogeneous and monodispersed samples. And this can be by gel filtration, SEC-miles, DLS, whatever. And then we do all the rest, which is freezing, negative stain. And eventually, when the project is good, then it will be pipelined into a cryos user session. And with that, I would like to switch to EMBL. At EMBL, we have 8 research groups. It's actually directed, as you showed previously in the slide, it's just next to the ESF. I'm sitting now in EMBL. We have 8 research groups, and at the moment, 30 cryo-EM users, more or less. When I started in 2017, actually it was less than a handful. So there was a lot of training and teaching involved at that time, and also installation of all the instruments. And the scientific advisory board meeting, which we had in 2017, actually advised us, luckily, to have our own autoloader equipped instrument with a satisfying camera. So that was when we started to install the glacius, first by room preparation, 2 months. This took 2 months, and 3 to 4 months later, after the delivery of the glacius was operational. And what we have internally now is actually a T12 microscope, for screening and mostly also for training users. And then for independent users, they use the glaciers for screening and data collection. And successful samples within EMBA Grenoble then mostly go to ESRF or to Heidelberg for data collection on a more high-end instrument. And also it became quite clear that we need more human manpower. So initially it was Wojtek and me supporting the users in EMBA. And recently in September 2020, Sarah joined us, and she's now helping users on a daily basis, especially as I'm very often in ESF and then not available for EMBA. She did also the recent benchmarking after the upgrade of EPU with apoferritin sample. She tested both in linear and counting mode to compare, and she got quite some satisfying result processing the data in CryoSparks. So we were quite happy to show that to our users. You saw already in the last talk, you saw WARP. We actually use this very happily in EMBL for all our pre-processing and particle picking on an external workstation. After particle picking, mostly users then go to Relion or CryoSparks for further processing. And yeah, we had good success with that to real-time monitor what's happening on the microscope. And since the installation, we had already quite some nice results from our instruments, also with data collections in ESF and Heidelberg. For example, on RIC2, which is important for immune pattern recognition, the before mentioned influenza polymerase, different structure snapshots, CJ calmodulin, which is important in Legionella pneumophilia, and also cohesin ATPase, explaining the SN-cyclising ring opening, and the later to be mentioned SAM1. And with that, I would like to talk shortly about a project which I'm very proud of to be involved in. Our instrumentation team here in EMBL, they, which was led by Florent Cipriani, and it's now led by Gabriele Papp. Since the very beginning, I was part of that and helping them in the setup of an automated grid preparation process. And well, I have not time to go into the detail of that, and it would be a talk on its own, which deserves also to Gabriele, who is our main engineering brain behind this. The idea of this machine, and there are already other machines out there on the market. We are not the first, but still we make quite some good success on that. So within the one machine, we have a plasma treatment, then a picoliter drop dispenser. We can go up to 1.5 picoliter. Then a fast Beeson-Bob jet freezing, a quality control step for the ice thickness, and then a storing unit where we can store a multitude of grids. And this would replace the error-prone manual vitrification process which we have at the moment. And we test this system internally at our microscope. And what we did first was actually just shaking the ice thickness measurement tool, which was more than a year ago. And very recently we did our first reconstruction from a grid which was prepared on that machine. There was still a resolution limit, which was basically by the ice thickness, as you can also see here on the slide. In our prototype, the spreading of the droplets was not yet optimal, but in the second generation instrument, which we are building now, we believe to have solved this issue, and we should get much thinner ice and also better coverage on the grid. And yeah, and with that, I would like to continue with the main part of my presentation, which is a short story of SAM1. And this is a collaboration with Hjartan Opatowski from Israel with whom I'm working, both involving EMBL and ESF. And someone is the most evolutionarily conserved member of toll interleukin receptor family. And so it's just 8 to 9 years where all its functionality had been resolved. So I will make a short overview of the history of it. So actually, there's a multitude of stimuli leading to neural cell death via different pathways, and extrinsically, intrinsically, and for example, here by TNF-alpha. The problem here is that you have all kinds of different mediators and also different inhibitors. So there's not one omnipotent way to address or inhibit them in some pharmaceutical way. However, in 2012, it was found that a certain type of axon degeneration, which is known for a long time and called Wallerian degeneration under mechanical stress, does not involve any of these before mentioned pathways, but requires someone. And this was an important finding. So there were tests where they cut the neurons, and then what you see is actually the fragmentation of the axon. Moreover, in 2019, it was shown that knockout mice, which appeared to be normal in lab, were protected from Wallerian degeneration, not only by the severing of the axon, but also by various other induced stress events like viral infection, hypoxia, peripheral neuropathy, or inflammation. So that finding stresses that someone plays a quite central regulating role of the axon fate under stress and might be potentially an interesting drug target. SARM1 has 3 domains, ARM, SAM, and T domain. In 2015, it was found that with a very elegant rapamycin-induced TEF cleavage construct, that indeed also in the cell without a mouse, they could stop the axon degeneration. And they found that actually the triggering moment is the tear dimerization, also with this rapamycin-induced reporting system. So you need a tear dimerization, which turns out to be quite important in order to perform the NADA's functionality, which again triggers the axon degeneration. And this is naturally somehow depending on the here mentioned SAM domains. In 2017, the same group found that it was the tear domain itself which had NADA's activity. And this was a very surprising finding because tear domains were known for protein-protein interaction and an innate immune response, but not so far as an enzyme with having an enzymatic function. And now it's known that in bacteria and plants, many tear domain containing proteins or related proteins to SARM1 have this functionality of an enzyme. But this was actually the first time they found this, and they defined the enzyme kinetic parameters of this with a Km of 24 micromolar and a K cut of 10. And very importantly, they found also that the ARM domain is inhibitory to this action. And so to summarize, we have an autoinhibition by ARM, SAM 1 and 2 unit, which allows dimerization to perform the action, and then an enzymatically active tear domain. And so this was again the first tear domain to be found. They believed that it was part of a ancient cell death pathway. And at that time, it was not yet completely understood if this action was depending on intercellular calcium mobilization by the products, or if there was some kind of energy failure happening based on NAD depletion or electron donor activity depletion. And before I joined the project, Chiara and his colleagues, Mike and Julia, they studied the crystal structure of tandem SAM domain, which you can see here. And they found that it forms a closed octanaric ring by the electrostatic charges and hydrophobic interactions. And only SAM1 appeared to be critical for the swing formation, while the SAM or SAM2 confined it into one plane. And they identified this by comparing it to other single SAM domain containing proteins, where they see that it forms more likely a spiral instead of a planar ring. What they showed next is actually that the SAM tandem forms an octameric structure by segmals, and that the same kind of octameric arrangement is also there in the full length SAM1. So this they could then also validate by negative stain EM, where they got these very beautiful class averages of inner and outer rings. And they could already get some ideas about the domain organization in there. So, and this was the point where I joined the project. However, when we wanted to go to Cryo-EM, what we saw at first was not looking like that. It was not as optimal as we would have expected. The outer ring was not visible in Cryo-EM. What we saw resembled more like the inner ring, SAM ring arrangement than the complete SAM1. And only maximum 20% of particles contained the outer ring. So we needed to decide if we want to have very long and complex data collections and sorting out a lot of particles, or if we can somehow optimize the sample. Our first approach was indeed based on a very well-known technique, which is called graphics. So we just did some cross-linking and had some success with this. We got much more particles which were in a closed conformation. So we believe that we shifted somehow the equilibrium into a more closed conformation. And
sorry, you have 3 more minutes.
So this allowed us to generate the first structural model fitting arm domain de novo and some anterior domain. I will not go into this detail yet now of the structure. However, most important, we saw that the tier domains are actually kept apart. And this turns to be very important because this seems to be rather an enzymatically inactive SAM1. And also the resolution of this one was limited, especially in the outside of the structure. So we first of all wanted to understand why we have this open and closed conformation, and also what are the driving forces of these states. And we found that to study this hypothesis, we first did some mutational experiments that we could show that the interaction side of the arm, the tier docking and the arm docking side are indeed important for inhibiting the tier domain. So we had in this cell viability assay here, so inhibited molecule, but actually in wild type we saw something different, which is a more active molecule. So we were asking ourselves why we see an in-cell inhibited molecule, why when it's purified it turned out to be more active. In a very similar experiment, we tested in a cell viability assay in cell the enzymatically deactivated mutant, and this little contradictory which we had, so we could really show enzymatically that in vitro we have an active enzyme. We could see by kinetics and HPLC that our enzyme is functional, while it was not in cell. So we wanted to understand what is the action of that. And there are known studies that phosphorylation or NMN binding might modulates this. However, we believe that what our data shows is there's rather a factor, an inhibitory factor, which is removed during our purification, which defines that what we see in vitro is a rather active state. We tested a lot of molecules like ATP. In the end, to make the short story, the long story short, we had we found that NAD itself confines the conformational change, which we see already in the micrograph. And in 2D classification, it became even clearer that we have an inverted situation when NAD is added compared to having no NAD. And also we could verify this finding enzymatically, where we see a bell-shaped curve in a fluorescence assay of the substrate inhibition giving higher and higher concentrations of NAD+. And also by comparing HubeSum1 in this HPLC-based assay for with having low amounts and high amounts of NAD, with standard NADAs, we could see in the standard NADAs case, there is no impact of the NAD concentration on the enzymatic activity, while this is clearly the case for HubeSum1. And we got a much better structure from that than previously by graphics. So most likely because this was a much more natural state of the structure than we had before. So we see also the local resolution is much more homogeneous than before. And we could find that there's a NAD bound in an unexpected site of the structure, not in the catalytic site, in the tear domain, but connected between the arm 1 and arm 2, which you see here. And so we were quite sure that this is NAD. And we did some mutational studies where we could show that indeed the interacting side chains which stabilize this NAD, if they are mutated, we get a situation which is very similar as if we would have removed the whole arm domain. So we get a very active SUM1. And so with that, we derived the model that NAD is depleted by some stress event, and this would activate and induce SUM1 to itself become active and further deplete the remaining NAD and result in an energetic and catastrophe and axon and cell death. So, so it's basically substrate inhibition, which we have in a healthy neuron. And then if I have a few seconds left, I would just like to show,
really.
Not really. So just to shortly mention, I have a collaboration with Konstantin Boyko in Moscow, actually, on butyrylcholine esters. And this was a project which was already 2 years ago. We were at the time a bit resolution limited, so we didn't reach that high resolution, especially as we had a quite competing situation. We couldn't collect more data, but still having a low resolution model of that, we understood the structure of the butyrylcholine esters much better than before. They were before just crystal structures of the monomer, but not the full structure of the highly glycosylated tetramer. And there was a MD simulation of that, but we could actually falsify this MD simulation, as you see here, with our low resolution model. So we see that here's a tail which is sticking out in the MD simulation, and in our flat, in our structure, it turned out to be in the center of the dimer of dimers, and that the conformation is in a non-planar conformation of this tail. And on top of that, they did some MD simulation modeled in the glycosylation, which we actually couldn't see in the structure. And validated this by SAX measurement, that it's actually a much better model than the previously old empty simulation. So even sometimes with low resolution models, you get some nice information. And with that, I like to acknowledge and thank many people with whom I've been working. And for the SAM project, especially Jan Opatowski, which was the main part of my presentation.
Yes, Michael, thank you very much. So we actually quite a little bit into our first break. So everyone who wanted to have a coffee break, you should go to your own kitchen, take your own coffee, unfortunately, because, but in the meantime, and be back, yes, and be back at 15:15, where the next speaker will be online. But I believe that in the meantime, we can ask the question from the YouTube, from Leonid Sazanov. What kind of time resolution is expected with a time-resolved application on EasyGrid?
That's a very good question. So in EasyGrid, so what I can tell you is just that our we designed the instrument in a way that our the freezing step after application is very fast. So we go we move the grid with a speed of 1.5 meter per second into the plunging. So it's a question of milliseconds then which we have. But indeed, yeah, I mean, it's a question about all these conformational changes which can happen in at the air-water interface and before actually the freezing takes place. So that's a very important question.
Okay, thank you very much. So yes, thank you again for your very interesting talk. And next speaker, next session will be in 10 minutes, 15:15, and the next chair will be Grigory Sharov from MRC, who actually is the, he was my undergrad 10 years ago. So I would like to meet him again online. So right now we have just a short break. See you all later. Bye-bye.
Bye-bye.
All right, welcome back, everyone. I want to greet you coming back to our next session. We have our more exciting talks to hear, and our first speaker is going to be Garib Murshudov, who is a professor at University of Cambridge. He also leads a computational structural biology group at MRC Laboratory of Molecular Biology. And his group research is mostly centered on the development of various mathematical, statistical, and computational tools for both macromolecular crystallography and cryo-electron microscopy. So without further ado, I would like to pass the floor to Garib.
Great, thank you. Thank you for the introduction. And I would like to start with thanking the organizers for inviting me to give a lecture with a fully packed with the exciting speakers. And I hope that at some point pandemics will end and we'll do this type of conferences in Moscow. And I have not been in Moscow for 28 years. So just a little bit corrections that I'm just a group leader in MRCLM, but I'm not the professor. That is besides the point. So as Grigory said, my talk, my group is concentrated on method development for Cryo-EM and crystallography. And that's why my talk will be about the methods, not about particular structures, but about the methods and how they can be developed and used for math calculations, improvement, modeling, refinement, and so on. So I will talk first about the one particular things in crystallography, p-values and maps in crystallography, how p-values affect the maps, and then I will go to Bayesian estimation and what is the meaning of that, and then I'll go to signal to noise and signal and noise in maps and how can we estimate them. Then p-values from local correlation. I'll give some details, but I have some formulas, but that you can ignore them. They are not important. Important is that things that intuitively what do they mean. And at the end, I'll talk a little bit about hydrogens in Cryo-EM maps, which 10 years ago was considered as a crazy thing to think about. That you can see hydrogens in Cryo-EM maps. Now it is becoming routine. So map quality depends on local mobility of the molecules. But essentially, it means that the quality of map depends on signal strength as well as noise strength. And we can, even if we reduce noise level, still there are the problems that there could be because of mobility, because of partial occupancy and so on, there could be a lower signal strength, and that affects the map quality. So if we calculate average local maps, then it should reflect our average signal. Also, if we calculate local variances at each point, then a higher local variance means that a higher signal, lower local variance means lower local signal. In crystallography, we update maps as models become better. The main reason is that we do not have phases. We have to calculate phases from atomic models. In Cryo-EM, we do have phases. However, Fourier coefficients as a complex variable, they are noise. They have noise in both real and imaginary or amplitude and phases. So I will just tell a little bit that how can we account for this fact. So p-values, and that is one of the things I was thinking for some time, and at last we have finished this particular project. So p-values should obey inverse compound distribution. The reason is that p-values are variances of atomic positions, and variance, obviously, variances include the mobility of atoms as well as inaccuracy. And it turns out that this hypothesis is quite well, it works quite well. However, there are cases when p-values may have p-value distributions may have two or more modes. Usually it means that one part of the map or one part of the molecule is well-defined, another part of the molecule is less well-defined. Another less well-defined part of the molecule obviously will have a lower density, lower signal, lower density, and that's why details will be less visible. And if you go further with that, and there are cases when we have that is in crystallography, then we have a well-defined part and not well-defined part. That turns out that in some cases, just by looking at the p-value distribution, we may be able to say that which part of the model is wrong. I mean, for most people would say that this part of the model is at least less likely to be there than other parts. That is fine. That is in crystallography. But similar things happened in Cryo-EM, that we have a different part of the molecule that have a different mobility. Now, question is how can we account for them? So let's just start with saying that for Bayesian estimation, we need two types of probability distribution. One, the probability distribution is conditional probability distribution of observations given model. A model, in our case, atomic model. Model could be different things. In this particular case, it becomes that as two-dimensional normal or Gaussian distribution with certain variances. Variances are components from contribution from noise and signal, noise and unexplained part of the signal. That is, we'll come back to that a little bit later. Second type of probability distribution we need is a posterior probability distribution. That is what we want, a distribution of what we want to estimate, that is true map, given all information we have. All information we have at the moment, observed map as well as calculated map. It turns out that it is also two-dimensional Gaussian. Now, it essentially means that when we do modeling or modeling of atoms or refinement of atoms, after that we should be able to calculate a updated map that would reflect observed as well as calculated maps. That essentially, what does that mean? That if we would have a no noise, then we don't need any contribution from calculated maps. But if we do have explained everything, our signal has been explained completely, then observed maps is not needed also. We need only calculated. That is an interesting thing, but we have to be careful with that. This part of the work will be available when we are sure that misuse of this type of calculation is less likely. But we can use this type of formulas immediately to calculate for difference maps. And now, if you look at here, what we see here is that we have several components. We have a unexplained signal variance, noise variance, as well as a sharpness that is parameterized by local p-values. And to calculate beta maps, we should be able to estimate all these quantities involved here. Now, how can we estimate those quantities involved there? Some of them can be estimated just by calculating difference, but there's another interesting way of calculating of the local signal and local variations, that is using a local correlation. Essentially, it is what is that at each point we take certain kernel and calculate correlation between two entities. It could be between two half maps or between observed and calculated maps. And then we move that local kernel and we calculate at each point a correlation. And that correlation depends on signal and noise. And now it has different, this type of correlation correlations have different interpretation. When maps are half maps, then this correlation means as local signal to noise ratio. If maps are model and observed maps, then this correlation means that where we have more or less errors. If these maps are two related maps, liganded or unliganded maps, maps for liganded and unliganded molecules, then it means that how much common signal we have in two places. This kind of calculation or correlation can be used immediately for validation. That is data taken from the EMDB. And on the left side, what we have is that map model correlation. This coloring, observed map is colored using a map model correlation. It means that part of the map has been described, but part of the map has not been described. And in the middle, we have a half map correlation. It means that we have signal here, but there's no model. On the right, a model is colored by map model correlation. It means that this red part means that we have error. So by looking at this correlation and mapping these correlations to coordinates, we should be able to say that which part of the map needs to be explained and which part of the model has errors. You can use that to identify a unmodeled part. For example, in this particular case, linoleic acid. And for map model correlation, we see that there's no model, but there's a signal. And if you put the model into the signal, then into the map, then we get that map model correlation becomes higher. It means that we have now described the map using the atomic models. But it is fine. It is available at the moment. Can be used, but what we would like is to see that can we use that to calculate a local p-values, local signal reduction. And it turns out that after some algebra, it becomes that a local signal variance is related with some kind of function of total correlation and local correlation. All of them can be easily calculated using a seconds or minutes. So this formula gives us a estimation of a local p-values in the map. We do not consider at the moment atomic model. That is Cater has already implemented that, and if you look at this local p-value estimated using a local half-map correlation. It obeys, as I said before, the inverse gamma distribution. And that is a p-values from atomic models. It looks like that the p-values from atomic models are larger than they should be. And the reason is that the atomic p-values not only account for local local variability, it also accounts for errors in the atomic models. Now, the natural question is that can we use these two type of p-value estimations and estimate errors in the atomic models? That would be, if we can estimate the local errors in the atomic models, then we can use it to improve the updated map calculations. That is just it to show that the estimated atomic p-values and estimated local p-values and atomic p-values, they are the linear relationship between them. Well, that is interesting. It means that we are in the right track. So now, people who are using single particle cryo-EM, they may have seen that in many cases, what we do is that we use a sharpened maps, weighted and sharpened maps. Weighted and sharpened maps, they highlight, enhance features in good or average part of the maps. But if you look at the outside of the model, the obvious outside the model, because of various reasons, the mobility will be higher. Mobility is higher means that we see less features. More precisely, we see broken maps. If we use that estimated p-values and they do local weighted and sharpened map, then we see that we can see sufficiently well this helices, and moreover we can see that there's some difference maps show that there should correct the model. So using a local p-value estimation, we can improve and calculate local weighted and local sharpened maps. And so now our next task is that can we use these local estimated p-values and local estimated errors to update maps, to more precisely to remove the maps in Bayesian sense. And if you can see that by map calculation as a decision-making problem, and then expected map or best map is a weighted average of observed and calculated maps. But there's a certain danger that if we calculated maps that have been overestimated, then we'll have model bias. We would like to avoid that. To avoid that, we need to be able to estimate the local p-values and local p-values and local errors. And let's just come back to this picture. And in this picture, what we see is that local correlation between map and model reflects the error in the model. So we should be able to use that to estimate local error-related p-values. As I said, and it is well known that people consider atomic model. They have a p-values. P-values will have a two or more contribution, at least two contributions. One of them is the intrinsic mobility of the molecule. Another one is that the error in the atomic model. So our task is that to calculate error-related p-values and use them for the improved map calculation. And turns out that after some algebra, some analysis and algebra, there's some equation we can use to estimate. We can use it to estimate local error-related p-values, and all these quantities can be calculated from map and model. That this quantity is local correlation between map and model, and dependent on local p-values of the map, and that is a local half map correlation. So using all these quantities that we can calculate available information, we can estimate the p-values. And And the Kaiser has already implemented that, and as expected, as correlation goes down, the error b values go up, and it's not unexpected. So we can estimate this b values from map model correlation as well as map correlation. Combine all of them together, we can estimate local b values as well as local errors, and that is that those local errors map to atomic models. Here, blue means the b values are low, error-related b values, and green means that the error-related b values are high. As we could expect, error-related b values for this tryptophan is higher, and we also see that in updated map and difference map, we see that tryptophan should be moved away from this position. Similarly, we can say for this methionine or this region of the map and so on. So I will come to the last part of the talk, and the last part of the talk is about hydrogens, and the whole point is that if we want to see detailed features of the in the map, then we should calculate a very accurate Bayesian computations accounting for all information. Information in our case are observed maps and their local behavior and atomic models also. How much time do I have? I have, I think, enough time. 10 minutes, yes. Okay, so now let's just think about this. So far, I talked about how can we calculate, how can we extract local information using correlations, and then you use that for updated, improved map calculations, and also for difference map calculations. But now let's just think about a little bit different aspects of the Cryo-EM and in general for diffraction scattering methods. So what we know that X-rays sees electron density, neutrons sees nuclear of atoms, electrons see both electrons and nuclear charges. Immediately by looking at that, thinking about that, you see you can come to a conclusion that if we use only X-ray and electron diffraction together, then we may be able to calculate better nuclear positions. That is mathematically possible. Experimental is a different question. But another thing is that accurate difference maps account for all errors must be performed. Then we may be able to see fine features like hydrogens. Now let's just think about hydrogens. Hydrogens are electrons see both nuclear charge as well as electron density. And for hydrogens, we know that electrons are a little bit shifted towards the parent atoms. Nuclear and electrons are away. There's a certain distance between them. So we know that electrostatic potential and the charge distributions are related by a Poisson equation. And in Fourier space, it just means that we need only X-ray form factors to be able to calculate electron form factors. It is good, fine for all other atoms apart from hydrogens, because all other atoms have electrons and nuclear charges are most likely to be on the same position. For electrons, for hydrogens, it is not like that. For hydrogen, what we have is that there's a shift, and that shift means that the form factors for hydrogen should be a complex numbers. And that complex number depends on the shift, on the distance between electrons and nuclear position. That's just graphical representation of that. What does that mean? And if we think about that, when we do observations, we calculate maps, then our maps is limited by the resolution, and also our atoms have our atoms also have p-values. It means that by looking at a little bit mathematics, we immediately come to conclusions that when we use electron diffraction or electron scattering, hydrogen position should be shifted away from parent atoms, and that shift depends on resolution. At 1.2 angstrom, we have small shift. At 2 angstrom, we have a large shift. And that shift also depends on p-value of atoms. It makes sense because the p-value, higher p-value means a lower resolution also. These two things have a very, very similar effect. So at 2 angstrom, we could see around the 0.1, 0.2 2 angstrom shift of them, even more than that. Shift of the observed hydrogen positions. It doesn't mean we are not careful. And if you observe those hydrogens, we may say that these hydrogens are moved away from the parent density. But that is the nature of the experiment we are using, nature of scattering, physics of the scattering, and mathematics. So we looked at Cater looked at a few cases at 1.2, 1.8, and 2 angstrom. And at 1.2 angstrom, obviously, we can see very nice hydrogens. And at the moment, they are visible mostly for well-defined parts, but there are some hydrogens visible for less defined parts also. But if you go to 1.8 angstrom, we still see some hydrogens. In X-ray cases, to see hydrogens, you need a 1.2 angstrom. We believe that if we do experiments accurately, then we should be able to see hydrogens even at 2 angstrom. To be safe, we can say that at 1.8 angstrom, we should be able to see hydrogen positions. And that obviously is interesting for some cases, but if we apply this type of calculation for enzymes, then we may be able to extract some information about enzymatic reactions. So I'll come to the end of the talk. Yes, okay. Conclusions and future. The signal levels in density depend on local p-values and local signal levels. By then, computation might be able to allow map calculation, but we have updated, improved map calculations. At the moment, we have those calculations implemented in the server card, but they will be made available only after we have tested them very carefully. Because experience shows that anything we distribute, people start using it, and if what we distribute has not been tested carefully, then people misuse it. We want to avoid that. Local mobilities can be estimated using local correlations. Local errors can be estimated using local correlations. That is I think we see that now. We have empirical evidence for that also. Local correlation in Fourier space should give us direction-dependent resolution information. At the moment, it has been implemented, but it is not made available to the community yet, but will be available for the community. We should be able to calculate a direction-dependent resolution, and if we can calculate direction-dependent resolution, then we should be able to use that for direction-dependent map sharpening, and also direction-dependent weighting and so on. That is, I'm excited about it, but that is an interesting thing to go forward for. So that's my last slide, and from MRC LMB, I would like to thank my group. And here I just talked a little bit about what Rangana is doing as part of a Wellcome Trust and what Cater is doing. And the first two slides were done in Baku, and that is my attempt to help to organize science in Baku, but moving slowly, but it's going there. So I would like to thank LMB for an outstanding working environment for CBM users, for regular feedback, and Jake and Toby for computing resources they support, and that's a fantastic resource. I would like also to thank obviously all these funding bodies, And I would like to thank you for your attention, and I'll answer to any question you have. You can ask questions in Russian or English. Well, thank you.
Thank you very much, Garib. So we have one question from a YouTube stream.
Yes, please. Yes.
What is your opinion on keeping the experimental map constant during model refinement?
Okay, let me just go back. Yes, and they talk about this part. Yes, and it is hidden here. In refinement, map should be constant. It should not sharpen the map for refinement. Yes, so and the noise level and the signal level should be part of the model. We want the model, I mean the probabilistic model. Yes, during refinement. But when we calculate a map, then we should update maps. Then we should use a sharpening, and we should use we should add information from the model as well as from observation. There are two different things, and often they are mixed. Because one of them is that what we want to do is to build models that describes observations as well as possible. Another one, we want to calculate a map that would be visually pleasing for us. There are two different tasks. Yes, and obviously they help each other, but there are two different tasks. So for model refinement, we prefer the unweighted and unsharpened maps. And that's mathematically, it seems to be like that. But for visual map calculations, we need to calculate as well as good as possible maps, and with enhanced features. Yes, that is a sharpening and so on. Okay.
Okay, there is one more question. Do you have a package that can be used online or loaded on a local computer or any teaching materials?
For teaching, we have all our software are distributed in previous life in crystallographic time. They were distributed by CCP4. So if you have CCP4, you have all our tools. Now, what we are doing is that now we want everything we are doing should be available freely. And that is why everything we are doing, and there are two tools I mentioned here, three tools in fact. And all of them are available from GitHub, and they can be downloaded anytime anybody wants. And there's ServerCAD, and there's also ServerCAD, and ServerCAD is also available from by archive. And there's also MDOM, and MDOM available for example from here. It can be downloaded and anytime could be used. Moreover, the source code is free, and they are under Mozilla license. Any part of source code can be reused without permission, without our permission. And what we want is that it not only develop ourselves something, we want also to promote an open source, open science, so that what we do can be used by others to move forward also. And we use other tools also. There are many things we use from NumPy, SciPy, and all kinds of things. Yes? So we want the open environment, at least for software development. Okay.
All right, thank you very much. In the interest of time, I suggest we move on to the next speaker. So thank you again, Garib.
Thank you.
Welcome back. So our next speaker is Alexander Sobolevsky, who is associate professor at Columbia University. And his group works on studying ion channel signaling using various biophysical techniques, as well as cryo-electron microscopy and crystallography. So,
thank you, Grigory, and thank you, organizers, for inviting me here. Yeah, it's a pity that we cannot be in Rio and Moscow right now, but let's just try to talk over Zoom. And I'm going to talk today more, like compared to previous speakers, not about the Cryo-EM development, more application of Cryo-EM to interesting biological program. And as you know, all of us from very childhood, we know the senses of cold and hot, right? But how we really sense it? And we, like, example is would be we touching something hot, right? And the sensation of hot goes through sensory neuron to our spinal cord, and in quick withdrawal reflex, it wires back to motor neuron and get a reaction of withdrawal. In more complicated senses, if we look at this area of the skin where we touch the object, we have a lot of different ion channels in the sensory neurons, which sense heat or cold. And what they do, they open their pores and depolarize the membrane of these neurons, and this electric signal actually get propagated in the form of action potentials to the spinal cord, where it can either form this withdrawal response or travel to the brain and form more complex reactions. Today I'm just gonna talk more about how it starts, right? How the molecules, the sensory molecules work. And as probably many of you know, that there are a bunch of temperature sensitive channels, and a big group of them are TRP channels, and there are several of them which are also called thermo TRPs. Interestingly enough, each of them sense temperature in a certain specific range, from noxious cold to noxious hot. And amazingly, is each of them is actually associated with some sort of chemistry, right? Small molecules which in us associated with our senses of smell and taste. So how these guys work? The examples for heat sensitive channels would be, let's say we stay at room temp, and in that temperature, all of them are silent. And then as temperature increases, at certain point, at certain temperature, the ionic current starts to raise up. And the sharpness of this increase is very high. So that basically defines the high temperature coefficient. Similarly, if we we have organ at the body temperature and at which the cold sensitive channels are silent, if we drop temperature down, at certain point the current starts to penetrate these ion channels. So today I focus just on one example of these channels, TRPV3, which is a heat sensitive ion channel. It expresses mostly in skin, also in several more organs, including brain, and therefore its functions are mainly associated with different physiology functions, and pathophysiologically it contributes to a number of mild and severe skin diseases, including those which are caused by mutations, which are called channelopathies. This channel also involved in several types of human cancer. So from biophysical perspective, as I told you, right, they can be activated by temperature and by ligands. And one distinct property of these channels compared to other temperature sensitive channels is that in response to a repetitive application of stimulus, these channels sensitize, meaning that you can see in response to this repetitive temperature application, current, the consecutive currents increasing. Normally, ion channels show the opposite tendency, which typically called desensitization or inactivation. So similar observation can be made for ligands, and here's the example of currents in response to chemical 2-APB. So this is a small synthetic molecule which is which activates or inhibits many channels. But I also placed a number of examples here, which many of you would recognize natural compounds. So in the era of resolution revolution, we started to work on these channels and got this first map of wild-type TRPV3. we built the model, and for those of you who are familiar with TRP channels, this looks pretty similar to TRPV1 channel originally solved by Efian Chen and David Julius. And in essence, it has this transmembrane portion, which somewhat reminds the structure of voltage-gated ion channels, and characteristic of all TRPV channels, this large intracellular skirt, mostly built of ankyrin repeat domains. I want to just point out two important features in this molecule is that each of 4 subunits of this molecule has these 2 pronounced lipid densities, we call them 1 and 2. And also, this was first structure where we see the C-terminus, which wraps around the 3-stranded beta sheet, which connects the elements of the skirt. So these elements will come up later when we talk about temperature sensitivity. Now, for the first structure, for the apo structure, we measured the radius of the pore, and while the upper part is conducting 4 ions, the intracellular part of the channel is blocked by side chains of methionine 677, which create this hydrophobic seal of the pore on the intracellular side. Obviously, we've been interested to find out how this channel open, because that's the main function. And we started with opening of this channel by the ligand to APB, which is the highest affinity ligand of these channels. And you can see in this experiment, as we apply 2-APB with increase in 2-APB concentration, we can get more and more calcium getting into cells, which are loaded with fluoro indicator. We added this ligand to our protein preparation, hoping that we'll get open state right away, and that didn't happen. And one thing one trick we decided to use, and that was based on our previous studies of another representative of TRPV family of ion channels, TRPV6, which is not temperature sensitive. There we figured out how to use 2-APB efficiently is by introducing mutation in its binding site, which serendipitously increased affinity to 2-APB by about 2 orders of magnitude. So we looked at the sequence of these ion channels and found that the tyrosine, which we mutated to increase affinity in TRPV6, is conserved in the family of ion channels. And we thought, well, why don't we try to mutate it in TRPV3 also? We did, and fortunately for us, we've seen similar effect. Now, after we added 2-APB to our mutant channel, we got a structure which was somewhat different, and the difference obviously came from appearance of 3 densities per subunit, which somewhat reminded the molecule of 2-APB. And of course, you just see in Holger's presentation where this molecule would look much better in density, but unfortunately, this is low resolution structure. And to confirm that this density indeed represents 2-APB molecules, we've done a lot of mutagenesis and in each of these 3 sites, and confirmed that indeed these are likely 2-APB molecules. In fact, about 10 years before us, one of the sites was defined by Artem Patyan's group through scanning mutagenesis, which also confirms our finding. Now, when we measured the pore of this ion channel, it's clearly open, and you can appreciate it's open through. And besides, because of changes in the lower pore, rotation of the S6 helix, now the entire pore becomes electronegative, which must be very good for conductance of positively charged cations. Now, if you look at the binding sites of 2-APB, 2 of them do not induce much of the conformational change, but the third one, which is where the 2-APB binds at the top of S1S4 bundle, it actually pushes out the S1S2 loop, which resides there in apo state. and that kind of induces the conformational changes happening as a result. And these include rotation and movement of the P-loop helix, which form the selectivity filter of this channel. But most strikingly, changes happen in S6 pore-forming segment, where we see 2 helical turn increase in the length of the S6 helix, which actually coincide with shortening of the TRP helix. And because of this dramatic change in this kink, we have rotation of the TRP helices by about 20 degrees, and that in turn causes rotation of the S1, S4 segments around the pore module. In the contents of the entire molecule, that results in this rotation of the skirt by about 8 degrees around the ion channel, and the entire skirt sort of lifts up and gets closer to the membrane. Something which was not observed previously in other representatives of TRPV family of ion channels for which different gating states were available. So basically, our idea about gating mechanism of this channel as gated by ligand was that the 2-APB binds to its sides, and in particular the binding at the top of the bundle pushes apart the elements of the S1, S4 that allows to push out the lipid from the interface between S1, S4 and pore module, and get elements of the pore module around the gate get closer to the periphery, and that's what opens the ion channel. And in the Morph movie, you can clearly see how these changes actually result in lifting up the intracellular skirt and how it gets back upon closure. Okay, so what I told you about is gating by the ligand to APB. Now, more interesting part, how these guys respond to temperature. Well, to get more physiological biophysical insight, we collaborated with Eleonora Zakarian group in the University of Illinois, and her group did experiments, single channel experiments with TRPV3, and if you take wild type channel reconstituted in lipid bilayers, you can appreciate at 22 degrees we have basically no activity whatsoever of this ion channel, and if you raise temperature to 42 degrees, you can see a lot of openings. And this increase in open probability happens pretty sharply, and this point defines this high temperature coefficient, the characteristic of all temperature sensitive ion channels. Okay, so we have working protein, and we decided, okay, let's apply it to the grid, right? So we heated up the sample, applied to the grid at 42 degrees, and got 2 main conformations, which we called closed and sensitized. Well, as you can guess, closed name came from when we superpose our structure at 42 degrees, it's pretty much the same as structure I showed you before at 4 degrees, the apostate, similar location of lipids and very much similar conformation and sizes of the pore. Interestingly enough, the second one, which we hope would be open state, we call it sensitized. And despite there are changes like those happening upon opening, I described it before, happen in this, in the lower part of the pore. Despite these changes, the pore remains closed, and you can see the side chains of isoleucine 674 create a hydrophobic seal of the pore. Well, that means our attempt to open it up didn't really work that easily, and we thought, well, that's sort of understandable because, as I showed you before on the plot, the probability of opening even at high temperature is about 0.3. So in structural conditions, we somehow have pretty heavy bias towards non-conducting state. So what we've been thinking about is we should find modifications or tricks which would increase probability of opening and allow us to shift equilibrium towards the open state so that we can heat activate the channel and get it open. And so one of the ideas was, well, if our mutation, which I described before, which sensitized the channel to open it by ligand, maybe we can use same mutation and it might sensitize it in response to other stimulus, which is heat. And when Ella's group did single channel experiments, that's what exactly happened. So at 22 degrees, this channel already opened a certain probability, and at 42 degrees, it's increasing more. And you can appreciate the open probability is already pretty high at 20 degrees and goes up. And the slope is not that sharp, which defines this pretty low temperature coefficient, which is typical for weak temperature sensitive ion channels. Okay, so we got our candidate and we subjected it to the first to control experiment. So we subjected the protein held at 4 degrees to Cryo-EM, Plunge freeze it, and found actually amazing just one conformation. So at 4 degrees, protein held at 4 degrees basically stays in this conformation, which we call sensitized. And as you can guess, we call it that way because it pretty much the same conformation as I showed you, sensitized wild type at 42 degrees. Okay. Now the time was to heat it up, and at 37 degrees, we luckily seen 3 conformations, which we call sensitized, intermediate, and open. And as you remember, I told you before about C-terminus, and C-terminus in all structures I've showed you so far is wrapped around the three-stranded beta sheet in this configuration. And in the conformation we call open state, it unwraps, and actually, as other groups showed later, it forms this alpha helical portion instead. And interestingly enough, in intermediate states, we have 2 diagonal subunits having C-termini wrapped around and 2 in extended and unwrapped configuration. So here's the closer look. That's how C-terminus typically wraps around, and when upon opening it unwraps, this portion will further form alpha helix, and that space where the C-terminus was residing before, it's actually start to fill up with N-terminus unseen in the frozen sensitized structures. So both termini actually play important role in temperature induced gating. Okay, so of 3 conformations, sensitized one, the one we call sensitized, is very similar to other sensitized channels. You can appreciate the pore radius is nearly identical. And on the opposite side, the open conformation has this pore very different from sensitized and closed in this lower part. And this profile must remind you the one I showed you before, activated by 2-APB. In fact, if you superpose these 2 structures, they're nearly identical, of course, except the regions where 2-APB binds, so we don't see 2-APB molecules in our heat-activated state. Okay, so to sort of wrap up, what kind of conformational changes we observe with temperature? Obviously, a lot of changes happening in the lower pore. That's where the gate opens, and that connects to the TRP helix. And we've been wondering, previously, there was a lot of mutagenesis done in these channels. And one of the hypotheses about how this temperature-induced gating starts is people were looking for temperature sensor, right? The part of the molecule which induces these conformational changes. And one of the hypotheses was that this large intracellular skirt, which I showed you before, and unclean repeat domains could be those temperature sensors. In fact, if we superpose all our structures based on temperature on the unclean repeat domain, you can appreciate that the structure of unclean domain repeat domain is not really changing. So it's not a temperature sensor. In fact, only portions which connect this domain to others, particularly to the pore, and this include TRP helix, this linker domain, the PS1 and linker helices, and also three-stranded beta sheet, and of course CNN terminus. That's what moves a lot. And another element, a critical element, and you can appreciate it from the top view, is the lipid. In a closed and sensitized state, we always see the presence of lipid in what we call site 1, and when the channel opens in response to heat, this lipid isn't completely gone. So this, interestingly enough, this lipid is, the site of this lipid is the same as the vanilloid site, what's called vanilloid site in TRPV channels, and here's an example. So it binds capsaicin and RTX agonists, or in apostate it binds this phosphonazitol lipid. And earlier, David Julius and Feng Chen group proposed that this particular lipid, its motion can be involved in heat sensation of TRPV1, and that's what we essentially confirm with TRPV3. And here's the wrap up with using the morph movie, how this gating happens, and essentially I want to emphasize the important role of lipids in this process, and also the C-terminus in this case illustrated. And as we heat up the molecule, you can appreciate the changes that are happening in the lower part of the pore, and especially significantly changes the occupancy of this what we call vanilloid site. And these all changes are kind of linked together. And now, upon cooling, you can appreciate that everything sort of goes back. So these are the main elements. They're all connected. And if we look at this molecule from the top, so that you believe that the channel opening is indeed happening. So in the pore looks closed in the closed state, and despite some changes already happening towards the sensitized state, the pore remain closed, and only the final touches, right, the complete removal of the lipid from the lipid binding site and unwrapping the C-terminal leads to the dramatic pore opening, and that what actually gives conductance through this pore. And so the remainder of the movie shows how the cooling actually brings it back. But so one point I want to make at the end is that using Cryo-EM, we visualize this region which are involved in temperature sensation, and these are several regions. And previous mutagenesis studies essentially identify all of them, but many times people would claim that this, by placement of mutation, the critical part of the protein, the corresponding part would be temperature sensing sensor. We more have this view right now that all these parts of the protein are linked together in some sort of conformational wave, and essentially the reason why many mutations throughout the protein can stir up temperature sensation, because it's like in a wave, you can stop the wave at any point and stop its propagation. And obviously many questions, even though we show this structural elements which involved in temperature sensation, many questions remain open, such as whether the wild type channels will show similar picture. Also the question about the trigger of these conformational changes, whether there is a localized temperature sensor or the temperature sensation is spread over this entire part of the protein involved in conformational wave. Also unclear what underlying energetics for this temperature induced conformational changes. And there are a number of theories, including this popular theory proposed by Clapham and Miller in 2011, that the changes are due to heat capacity changes, and other researchers favor the heat capacity independent conformational changes, such as energy, which coming from formation and breakage of molecular bonds. And so these are questions to answer. And at the end, I would like to thank people who actually have done the work, which I showed you today. Former lab members, Apu, who is assistant professor in IT Kanpur right now, Luke, who is a research scientist in Regeneron Pharmaceuticals. Current members of the lab who work on these programs, Kirill and Arthur. These are people in my lab. Our collaborators, Vicky and Roman, and members of their groups, personnel of Cryo-EM facilities, including Bridget, who's the next talk, and the different funding sources. And I would like to thank you all for your attention and happy to answer questions.
Thank you very much, Alexander. So we have a question from the audience. Although TRPV3 is considered as a thermosensitive channel, its function as a thermosensor in the skin is challenged. What is your opinion on this?
What is challenged exactly?
The function of the TRPV3 as a thermosensitive channel.
Well, yeah, it functions as a temperature sensitive channel. That's obvious, as I already showed in.
Yeah, that's a bit strange question, but yeah. Okay, since we are already over time, I suggest we wrap up and we come back in 10 minutes for the next session. So thank you very much.
Thank you, Grigory. Thank you all.
Thank you. Welcome back, everyone. So for our next session, we have two more talks today. And the first speaker is going to be Bridget Carragher, who is a professor at Columbia University. She's also a co-director of the Simons Electron Microscopy Center in New York. Most of you, I believe, would know Bridget from her continuous work on developing new methods to automate and improve the entire process, from specimen preparation to the generation of final 3D maps. And today we're going to hear about new approaches about sample preparation.
Thanks very much, and thanks for the invitation to be here. I would like to add my sad litany of regret that we're not all in Moscow. I was super excited at the idea of going there. I've never been. My husband tells me fabulous tales about how amazing it is. So maybe next time. It would be very enjoyable. So my group works on all kinds of things to do with automation, but given that you've heard quite a lot of other stuff today, I thought I'd focus just on Cryo-EM sample preparation. So in thinking about that, you know, we have to put this sort of into a pipeline. So the Cryo-EM pipeline right now starts, say, with a sample, although it has to be a very good sample, and ends with a density map and a model. And along the way, you have to make grids. You have to put that sample onto an EM grid. Then you have to collect a whole lot of data, thousands and thousands of images, and put it through quite a complex processing pipeline, and then refine and model. And other people will tell you lots more about these other parts of the pipeline as we go through the meeting. So just to put this in context, I want to say, where is Cryo-EM in 2021? And you've already seen this from Richard. We're doing extremely well. We're on an exponential growth curve here. Going on 7,500 or so structures now in the PDB. And last year there were 2,500 deposited into the PDB. So that's just amazing. But let's compare ourselves to X-ray crystallography. In X-ray crystallography, there's 150,000 plus structures, and they put in about 10,000 a year. So through 3D-EM, as they call it in the PDB, or cryo-electron microscopy, has a long way to catch up. we need to do better than this if we're going to make a really big impact on things like drug discovery and structure-based drug design. So where would we like to be? In summary, you can say we need to be better, faster, and cheaper. And in our group, we work on all aspects of this, trying to make everything better, everything faster, everything cheaper. But in particular, we work on specimen preparation because I think specimen preparation is the linchpin of getting better, faster, and cheaper. It's one of the most important things you can do. And I'll just emphasize today two regions where specimen preparation has a dramatic impact on overall throughput, and that's in ice thickness and in sample preservation. So first, ice thickness is absolutely key for data collection speed. The way we collect data, if you've heard from several people now, is we move the stage, the grid stage, to a new position. And then we, in that position, we can see many, many holes. And then we rapidly move the beam across all those holes, snapping out images. So the slow parts are moving the stage and settling down. That takes 30 seconds or so. Then you have to go somewhere and focus and check drift and things like that. That takes another 30 seconds or so. Then you can snap out these movies at about 5 seconds and hopefully soon less per image, per movie. So when you have a whole lot of beautiful targets like this with the ice is just right, and you can take a picture of every one, we get about 50 targets for every time we do these slow steps. But if the ice isn't right, if the ice is too thin or too thick, we get very, very few targets for every time we move this. And the difference is that here we're getting about 600 movies per hour, and here we're only getting 200 movies per hour. Unless you think that's not a big deal, that's like one microscope here and 3 microscopes would be having to run flat out to get you the same amount of data if your ice isn't perfect. So it really, when you say the ice should be better, like very controlled thinness, that makes everything faster, and it also makes everything cheaper because you don't need 3 microscopes, now you only need 1. So these things all swing together very much. And we see this every day in our lab. So we count the total number of images acquired in a 24-hour, and this is the number of images per hour. So you have a grid like this where the ice isn't great, and we're only getting a couple of 100 images an hour. You have a grid like this where the ice is very nice, and you're getting more like 400 or 500, and that means we're getting closer to 8,000 or so images a day. And if the cameras would be faster, we could go better than that too. So ice thickness is key for data collection speed, and it's not easy to get the ice perfect. Here's a beautiful example from somebody who used to be a grad student in our lab, Yongzi Tan, one of the very best cryo-EM people in the world. This is 2 grids he made on exactly the same day with exactly the same sample, exactly the same conditions within 10 minutes of each other. And they look kind of similar, maybe. And if you look at the holes where we're trying to find this thin ice, look kind of similar. But then if you look at the particles, these look a little better than that, perhaps. And in fact, this grid yielded nothing, just a blob, horrible, ugly blob, could never be refined. And this grid yielded a nice 3 angstrom structure, which subsequently went below 3. And the only difference between those 2 grids, nothing else changed except the ice thickness on this was much, much worse. Here, the ice thickness was about 20 nanometers, 200 angstroms, very nice thin ice. That's about the lowest we ever see it go. And here it was all over the show and we couldn't do anything with it. But these grids were made at the same time. So it's not easy to make beautiful and controlled grids. And the other thing, that might be key to improving data collection speed is the sample preservation. So one question you might ask is, well, how many images do we need under ideal circumstances? This is a pretty ideal sample. It's aldehydes. And if we look at that sample, with 10 images, we can get to a sub-3 angstrom map. And those aren't 10 great images. Those were the first 10 images we collected that day. That was a beautiful sample, just banged out 10 images, 3 angstrom map. So if we only needed 10 images to get to a 3 angstrom map, that's at 10 seconds an image or so. That's 2 minutes of data collection, maybe even less with the speeds we have now. So what's going on? The problem is most samples aren't ideal. And I'm going to show you some examples from a beautiful piece of work that Rado Danyev and his colleagues did, where they were comparing a whole bunch of different things for reasons of their own. But for us, it gives us some fabulous statistics to look at standard, typical data collection from a very, very good group. So this is very busy. Let's shrink it down a bit and let's ignore this column because it's a bit of an outlier. So here's Rado collecting data for GPCR and nice membrane protein over different circumstances. And what do they typically do? They are getting to a resolution of about 3, just like we mentioned before. So those are the kinds of resolutions they're getting to. But instead of 10 micrographs, they're using thousands of micrographs, 3 to 5,000 of micrographs. And out of those micrographs, they're picking millions of particles. And of those particles, they're only using between 5 and 20%. The others get discarded somewhere along the way. And in fact, if you wanted to just get to 3 angstroms, then you only need a few percent of these particles. But even if you're saying somewhere between 5 and 20% what are the usable images we get, we could take this 3,000 to 5,000 micrographs and turn that into 300 to 500 if they were all usable. We weren't throwing away so much data. And if you look at other experiments he did, this is a really beautiful paper. I encourage lots of people to go read it. It's the same story for these other examples he showed, basically using about 20% of the particles to get to the high resolution maps and less than 1% to get to just sub 3. And again, you know, that's if you're only using 20% of the particles, if you could use 100%, instead of 5 Krioses, now you only need 1 Krios. And given the extraordinary expense and rarity of these instruments for most people, this is a very big deal and we need to try and address it. So we started longer ago than I care to remember to try and find a new approaches to grid preparation. And we called this the Spotted On project. And the idea was that we knew that many people coming into our lab could collect beautiful data. We were going sub 3, you know, many, many years ago. But lots of people were coming in with really bad grids. And I often said in our facility, everybody's one perfect grid away from their perfect 3 angstrom, 3 angstrom map, or their very nice desired 3 angstrom map. And one of the reasons is it's making grids is quite a difficult process. So what we do to make a grid of thin ice with particles embedded in it is we put quite a lot of that sample onto a little mesh of metal with a holy substrate over it. And then we wick away most of the sample with a very gross sort of method, which means smushing blotting paper onto the grid. And as a result, 2 terrible things happen. One is that we've thrown most of the sample away. Almost all of the sample is wicked onto the filter paper and literally thrown in the trash. And the other problem is the grid can be very variable. I mean, the blotting paper is not very controlled. Bob Glazer recently did a really beautiful group showing at high resolution what that blotting paper is doing on your grid. So it's not surprising then that we don't get very repeatable ice. So the Spotted On project that we set out to do was meant to solve these 2 problems. In the one case, we would solve throwing away most of the sample by dispensing the sample in very, very small droplets. In this case, 50 picoliter droplets. Remember, in this usual way, typical way we do things, we put 3 microliters of sample on this. So there's micro to nano to pico, that's 1,000. So this is a lot less sample. This is almost no sample. From 3 microliters, you could make thousands of grids using just a few 50 picoliter droplets. And then we tried to find a way to not have this irreproducible ice by having the grids do their own wicking, so developing these self-wicking nanowire grids. So we built a robot to do this. That robot was built a long time ago. The robotics turned out to be the easy part. The self-wicking nanowire grids took us forever to discover. But basically, this is what the robot looks like. And the guts of it here is this piezo dispenser, which is going to spit out little droplets of sample. This is the sample at 50 picoliters being spit out of this. And then we do it just the standard way. Here's the grid. The grid goes flying past that piezo device that's spitting out sample. And so we get a wet row of squares splattered across the grid as it's whirling past, and then it gets put into the ethane about 100 milliseconds later. Okay, so that's what that looks like. And then the self-wicking grids, as I said, it took us forever to discover these. We tried about 1 million other things to try and get the ice nice and thin. I have the absolute greatest admiration for Jacques Dubochet because it's a really hard thing to do, to vitrify a thin layer of ice. So I think it's just extraordinary that he worked this out so well that we still use basically the same technique to this day. Anyway, so these are what the nanowire grids look like. They're just copper grids. You expose them to a simple chemical and they grow this beautiful bowling green, even layer of nanowires all over the copper. So then what Spotted On does, We have a substrate, a Holy substrate. It can be gold, it can be carbon, it can be regular holes or these irregular holes. And then we spray the sample at it. And here I'm just holding everything still and showing you what a video looks like as the sample hits the grid. And here's a still frame of that sample. So more or less what's happening is these spots hit the substrate. They start to spread out under their own momentum, but then the instant they come in contact with the nanowires, they get whisked away by capillary action. And what's left behind is a nice thin film. And that's shown here for a couple of proof of concept projects. So the drops are sprayed across the grid, and we're going to collect data on those wet squares, and you can get, a 2.3 angstrom map or sub 3 angstrom map for various test samples. So we set out to build Spot-it-on partly because people were having trouble getting reproducible grids reliably. But there are also major other issues with grid preparation that you've heard from several other people at this point. Particles often aggregate in ice. You get a beautiful negative stains grid, and then when you put it in ice, it aggregates. Particles can adopt a horribly preferred orientation, and you'll hear more from Dimitri in a little bit, how he has methods around that, but it's always a problem if it goes that way. Sometimes the particles won't go into these open space over the holes, they stick to the substrate. Particles can be partially damaged, and particles can be completely denatured. This is enormously frustrating. It looks great in stain, put it into ice, you don't see anything. So, as Bob Glaser has been telling us for years, and actually as Jacques Dubochet clearly told us in the very beginning in that very seminal paper in 1982, air-water interface is going to be a problem for Cryo-EM. And that's because our samples are mostly seeing surface. The volume is very small, the surface area is very large, as opposed to proteins in bulk solution. And what happens when they bounce around under Brownian motion in these thin layers, they end up sticking to the hydrophobic air-water interface. And a postdoc in our lab, now a group leader in our lab, Alex Noble, did a ton of work on this. He basically took tomograms of, 50 different single particles structures. We'll just zoom in on a few. But the bottom line was, indeed, yes, all your proteins are stuck at either one or both air-water interfaces. And so, whatever happens to them at the air-water interface, you are going to be seeing in your single particle reconstructions. So it turns out that Spot-it-on can help reduce some of the problems at the air-water interface. We believe that this preferred orientation that we see for many proteins, this is hemoglobin, which is sort of pathologically preferred. If we take pictures of this and we go into 2D class averages, we mostly just get one view, and it's sort of stuck at its hydrophobic patch at the air-water interface. If you use Spot-it-on, because we have the sample for much less of a long length of time in a thin layer, here, it's seconds if you're using a Vitrobot or something, and here it's 100 milliseconds that those particles are exposed to that thin layer and therefore hitting the air-water interface. As a result of that, we can see many more side views of the protein. I guess they just don't have time to sort of reorient and stabilize at the air-water interface. And the difference then is getting an ugly mess here that's completely wrong versus getting a correct reconstruction from this, because you need those side views. Even if there's only 20% of them, it's good enough to get this reconstruction. It also can help reduce sample denaturation in some cases. And this is work from Wei-Zhen Tang, the University of Chicago. And he was looking at pre-sequence protease. It's about 110 kilodalton protein. And what he found with the Vitrobot, if he's making these samples with the Vitrobot, most of them are denatured. He has to just throw away most of them, and then only about 15% of his proteins are in the state that you can interpret them. If we switch to using Spot-it-on, or the commercial prototype, in this case, Chameleon, then most of his particles, more than 50%, are in the fully assembled state, and he only gets a smaller population of denatured. And as you're going to hear from Carolyn Luger tomorrow, I think, she was working on a very beautiful structure called FACT, and I'll let her tell you all about that. In the Vitrobot, even though you can see FACT nicely in negative stain, you put it in a Vitrobot, nothing, completely denatured. If you switch to using Chameleon or Spot-it-on or Chameleon prototype, it's still not great, but there are at least particles there and enough of them that you can get 2D class averages and form a 3D structure. So it does reduce the denaturation, even if it doesn't completely fix it. And then there was a whole bunch of other structures also done with either spotted on or the chameleon prototype that we have. And a lot of these were done either because there wasn't enough protein available and you wanted to use very little, or to make it more efficient, or because of preferred orientation or denaturation, et cetera, et cetera. So the bottom line from all this is we definitely need to we'd like to keep our particles away from the air-water interface. Spotted on is only one way of doing that. Other people have used detergents. Some people have tried used graphene successfully, other substrates successfully. People have considered using sacrificial layers in closed systems. All of these methods are currently being developed. And the only problem is there isn't one golden bullet. Not one of them works for everything. So I think, this is under development, or maybe we just have an armamentarium of things that we will try. But whatever, if we can solve this problem of denaturing our proteins and having them in prepared orientation, we will definitely get better data, which will let us acquire it much faster, and that makes everything cheaper. So this is definitely key to doing all that. So the spotted on project has been commercialized into a product called Chameleon. This was our original concept in 2011. I can't believe it's so long ago that we thought of this. Most of the time was spent developing those nanowire grids. Chameleon is now available. We have a prototype in our lab, and I hope we'll be getting the proper commercial version in about another month or so. So what are we doing with spotted on in the meantime? So now that we have a Chameleon, we don't use spotted on to make grids in general. We put those on Chameleon. So what we've done with spotted on is turned it into a time resolved instrument. So time resolution, I think you've heard earlier today, you take two proteins, mix them together, and then put them into the ethane, which stops everything. So it's a mix and stop procedure. We can do that in spotted on simply by adding a second piezo head to this to the device. So we have one piezo head spitting one sample, another spitting another sample. As the grid goes past, and they mix within a few milliseconds of each other. And so as a proof of concept, what we have here, we deliberately split the samples at the beginning so we could sort of have the control on the same grid. And we just sprayed two standard samples, apiferritin and ribosomes. And if we look at this early part where they haven't mixed yet, indeed, you see the apiferritin. Over here, you see the ribosomes, but then when you, when you look later, you see the mixing. I'm not going to go back. You can see the two samples there. So that was a proof of concept for some real interesting examples. We worked with Israel Fernandez to look at ribosome biogenesis. So you mix 50 S ribosome subunits with 30 S ribosome subunits on the same grid, and it's about 150 milliseconds or so of mixing. That grid snaps into the ethane. So you get these 70 S ribosomes formed, and you get to see some of the intermediate states that the ribosome is in while it's forming that interface. So you can sort of study in a time-resolved way the biogenesis or the coming together of these ribosome subunits. Another interesting example is from Seth Doss' group at Rockefeller, and there what they want to watch is how DNA melts and how the RNA polymerase changes as these two come together. So what we do, and they're interested in these intermediate states, and one of the intermediate states they're interested in is at about 150 milliseconds after the combination of the RNA and RNA polymerase and the DNA. So that's perfect for spotted on. So what we have here is a control where we spat the RNA polymerase and, with a buffer, and then here's the RNA polymerase with the DNA, and you can see the DNA binds very nicely. And indeed, Seth and his group can see these intermediate states that they're interested in, and this work is ongoing and now in 3 dimensions. Another example, lots of people want to look at ion channels as they go through their opening and closing. Here's a calcium-gated potassium channel from Krina Nimijan's group. And indeed, again, with the control, if we mix the ion channel with a control buffer versus a calcium-containing buffer, we get different states of the ion channel, and you can see where the calcium is bound in some of these maps. Oh, and finally, we worked with Jenny Hinshaw and her group, and they are interested in looking how dynamin changes when you add ATP. You know, are there intermediates? You know, what happens? And indeed, you see a whole lot of really interesting, exciting things happen when you add GTP to these tubes, and they basically come apart and reform, and that works ongoing too. Okay, so that's the end of my presentation. I think I've got ending in plenty of time. So this is the amazing staff at the Simons Electron and Microscopy Center. We run various other centers there. We think of ourselves as a center of centers. We have NRAM, which is responsible for developing these new technologies. We have NCCAT, which provides access and training to the nation. We have NC2, which makes thin lamella for cryo-electron tomography. And we have the new Simons Machine Learning Center, because we believe that machine learning is going to be absolutely critical to making everything better, faster, and cheaper. We need to be able to, completely automate the data acquisition, because the cameras are so fast now. You don't leave a grid in the scope for days anymore. You'd really like to take it out after 6 hours. So you really need to know how good is my data after 6 hours. So everything will have to be far more automated. And then in tomography, the idea, as Dimitri spoke about earlier, I think machine learning is going to have a huge role to play there. So this is the group. We're a really big group, and lots of scientists helping users, as well as developing the new technologies, and lots of nice grad students and postdocs who are the engine that drives all of this. Okay, thank you for your attention.
Thank you very much, Bridget. So we have time for a few questions. The first question is it possible to make self-wicking gold grids?
Yes. I
guess what it means is not the layer of gold on top, but the completely gold grids, I guess.
No, because all plotted on grids are sandwiches. So even the ones I showed you have copper on one side and molybdenum on the other to make a nice smooth surface to pick up the substrate. But we've worked quite extensively to show that you don't need gold. You can use a gold substrate on a molybdenum or copper grid, or you could put a sandwich of copper and gold if you wanted. But it's not that it's gold mesh and gold substrate. It's the gold substrate on a metal mesh that really counts. So even gold substrate on a copper mesh, the thing doesn't move around and bounce around, at least in our experience. So we can't grow those beautiful nanowires on a gold mesh. In other words, we can only grow them on a copper mesh for now.
Thank you. Another question. If Spotitone makes a single row of grid squares with good eyes, wouldn't that be limiting throughput with ever-increasing acquisition speed?
Yeah, except you can get if every square is perfect and all the holes on every square are perfect, there's 20,000-30,000 holes on that row of squares. We almost never collect more than, I don't know, 6,000-7,000 images anymore. So that's plenty enough for a data set. If you had a very, very tricky project, maybe you'd put 2 straps down and then you'd have 60,000 targets. So there's plenty of targets. The real estate on a grid is just shockingly large compared to what we normally collect on. We collect probably a lot less than 10% of most grids, because most of the ice is terrible or too thick or whatever. And the new Chris Russo grids, where he swashes those holes in. I mean, you've got, I don't know, 1,000 holes per target or something. So you don't need too many squares to get your data. So I don't think that's a deal breaker, as long as you can get good ice.
Okay, thank you. Don't think we have any more questions from the audience. I guess we can move on to the next speaker. So thank you very much again, Bridget, for a very interesting talk. All right, so our next speaker is Dmitry Lumkis, who is an assistant professor in the Laboratory of Genetics at the Salk Institute for Biological Studies. And today we're going to hear about, I believe, the tools his group developed to evaluate local and directional resolution in Cryo-EM maps.
Okay, so thank you very much, organizers, for the invitation, and Grigori for the introduction. I'm going to tell you about some of our latest work on trying to understand sampling anisotropy and implementing tilts in single particle cryo-EM. So before I do, I just want to talk, reintroduce, I guess, or reiterate what Bridget has just beautifully described about sample behavior in cryo-EM grid. So if this is a cross-section of a hole in a cryo-EM grid, the way that we've always thought, or traditionally thought about how samples behave within the layer of ice is that they would be randomly oriented within that layer of ice. And we thought this prior to about 2018, when Alex Noble and Bridget came out with this really wonderful study showing that the reality is actually completely reversed. So they performed cryo-electron tomographic reconstructions of samples prepared for single particle. So they reconstructed these tomograms for about 50 samples or so, and just plotted where the particles reside within the layer of ice. And effectively all of the particles reside either at the top or the bottom, one of two air-water interfaces. There are a few exceptions here, but for the most part, the vast majority of the samples behave like this, at least using traditional methods, until Bridget can completely solve this problem. So the way that we've thought about these samples is that they would adopt random orientations, but in fact, nothing could be further from the truth. And most of the samples, what happens is, is that they actually adopt a preferred orientation. So this interaction at the air-water interface leads to preferred orientation of samples, and it could be one orientation or a few orientations. So one of the premises from this talk is that I'm going to try and convey is that reconstructions from preferentially oriented particles are unevenly sampled. What do I mean by that? What is sampling in the first place? Well, we know that a 2D particle image is a projection of the 3D object, and the Fourier transform of the 2D projection is a slice through the 3D transform of the object. Okay. And so this slice, samples all of the lattice points within along this region. Okay, so here's an example, a schematic of a slice, and this slice samples all of these lattice points in the transform. So when we think about sampling, we'll refer to sampling. Sampling is just simply an integer value. It's either a 1 or a 0 that it's evaluated at each one of these lattice sites, sampled by the Fourier transform of the projection. And so each particle, each projection provides some information about the Fourier lattice sites within this slab of points. And then if you combine these slabs into a three-dimensional volume, we refer to these volumes as sampling maps. These are volumes from thousands or tens of thousands of particles. So what are the properties and examples of these sampling maps? We looked at a number of different distributions. So if you have a uniform distribution of projections, okay, so these slices are inserted in a uniform manner into the transform, okay, and this is just a schematic of how the slices are inserted, and this is the experimental realization of the sampling maps. Now, if you have side views, then so these are perfect side views where your theta angle is 90 degrees. Okay, so then the slices are inserted parallel to the z-axis, and you have sort of an elongation. It's the sampling map looks cylindrical, at least at this threshold. If you threshold it down, it begins sampling more of the Fourier space. And then you can modulate the phi angle, and if you modulate the phi angle, you get a little bit some gaps in the sampling map. Okay, and that you can see here. In both of these cases are completely sampled. Okay, so every single lattice point in the transform has viewed a projection. So these are completely sampled, but they're not uniformly sampled. And there's an accentuation of sampling along the z-axis. Now, this is the bad case. These are the top views. These are the views where you have one preferred orientation and you have projections only along this cone. This leads to hypersampling near the XY plane, and it leads to missing information along the z-axis. Okay, so there's no sampling along the z-axis. We know that preferred orientation can result in loss of directional resolution. If you have just projections along these directions, so this leads to a map that is smeared and elongated. Bridget had already showed an example of one such map in the previous, if not this map in the previous talk. You have an elongation of the features. These are artifactual, and this has to do with the fact that you have limited or no information along the z-axis in the sampling map. Okay, we can evaluate these maps quantitatively using directional resolution, using 3D FSCs. And so we described these 3D FSCs a number of years ago, and actually a number of other groups had described similar sorts of implementations, in fact, over the better part of 20 years or so. It's essentially an extension of the conventional Fourier shell correlation analysis, except that you're looking in cones rather than in shells, and you can threshold the 3D FSC at an isosurface, or you can take a cross section and color it by the spatial frequency. And essentially, in an anisotropic case, you see that there's loss of information along the z-axis, whereas in the isotropic case, you get uniform resolution. We have a web server for calculating these 3D FSCs. All you need in order to do this is you just need your half maps and define your pixel size. We think these are very useful and really should be standard for validation. I think Gareb should have also talked a little bit about these similar sorts of implementations. All right, but for the rest of the talk, what I want to discuss is the effects that sampling has on global resolution. And this was a little bit unexpected to us when we came across it. The way that we came across it is by looking at a high resolution data set that we collected about 6 or 7 years ago. We had a high resolution data set of 60S ribosomal subunits. And at the time we resolved this data set to about 2.5 angstroms or 2.6 angstrom resolution. It was mostly, the resolution was mostly isotropic, but you could see that there was a few different preferred orientations that were characterizing this data set. And what we could do with this data set, because it was resolved to high resolution, because there was a few distinct orientation distributions, and you didn't need very many particles in order to get nice reconstructions, what we could do with this data set was subdivide it by orientation distribution. So we have our original 75,000 particles, and we take the first 10,000 particles that are characterized by a theta angle of less than or equal to 30 degrees, and that's orientation number 1. And then this is orientation number 2, so a different distribution, and then the third orientation, a different distribution still. And as a control, we could just take 10,000 particles that were randomly selected from the data, which represent all of the orientations. And the idea is that if the orientation distribution does not have an effect beyond the directional resolution, then these reconstructions should be similar or identical. But what we found was that when we plotted the global SSNR curves for describing these reconstructions, the global SSNR profiles were non-identical. And in fact, there was about a 6 or 7-fold difference between the best SSNR, okay, for the control case, and the worst SSNR for the highly preferentially oriented case. That was interesting, and Phil Baldwin and my group decided to investigate this further, and basically came out with this derivation. So just to emphasize, or just to bring up, the way that we've always thought about, or the way that cryo-EM reconstructions have traditionally been described, and this is for the better part of 40 years now, is that the resolution is related to the average number of times that the lattice point K is sampled, multiplied by the inverse of some per particle of this per particle SSNR. So this is an experimental envelope that lumps together everything about the data. So it's the microscope envelope, it's the camera envelope, it's the processing envelope, it's everything that describes the data. And the only thing that Phil did differently was he decoupled the sampling factor from this envelope, from the experimental envelope, and derived this geometrical factor that into the expression. This geometrical factor, we call it the sampling compensation factor, or the SCF. It's just simply the harmonic mean of the sampling. That's all it is. And it describes the uniformity or the non-uniformity of the sampling distribution. So we wanted to look at how the SCF, this geometrical factor, behaves for different types of sampling distributions. And we went back into these cases that I introduced. Okay, so these are all cases that are completely sampled. So every single lattice point has been viewed in the reconstruction. And so either the uniform views or the side modulated views. And this is a plot showing the behavior of the SCF geometrical factor for these different types of distributions. There's one more here. It's the complement to the cone that I didn't have in the schematic. The SCF, just to note, is simply calculated. It's just calculated from the Euler angles. Okay, nothing else goes in. It's just calculated from the Euler angles. And so for the uniform distribution, the SCF factor is 1. Now, when you go from the uniform distribution to the side distribution, okay, you transition through this complement to the cone. So this just means that you have projections everywhere except for this cone right here. It's better than side views. It's almost like uniform. So you try, and the SCF goes down from 1 to about 0.81. So exactly 8 over pi squared for the side-like views. Now, when you start introducing modulations to the phi angle, then the SCF starts to decrement really rather dramatically, rather quickly, depending on how deep these modulations are. And the idea that we proposed in that paper is that the sampling compensation factor, it informs how the global SSNR curves should be decremented due to the arrangement of projections. And so we showed that using synthetic reconstructions. So for example, for these side-like views where these are fully sampled reconstructions. Okay, so these are global SSNR curves for different reconstructions of the synthetic reconstructions of the HA trimer that differ only in the sampling or projection distribution. So if we look at this is the uniform case, that's the best. And now these are side-like projections, so that's a little bit worse. And then as you start introducing these modulations, and especially deep modulations, the SSNR goes down. And the idea that we showed was that the attenuation of the SCF is approximately related to the attenuation of the SSNR. And so if the SCF is 1 and the SSNR is also n, so then as you start varying the sampling and the orientation distribution, you can approximate the shift. So you can approximate or you can evaluate the shift from the SSNR, and the two approximately match up in terms of how the SCF describes the sampling distribution and the attenuation from the global SSNR. We also did this for top-like distributions. Okay, so these are the really bad cases where you have regions along the z-axis that are unsampled. And long story short is that the behavior is approximately similar. And so in this case, you're going from again, and then incrementally decreasing cones with some random sprinkles, throughout the rest of Euler space. So these attenuations, so the behavior is similar, except that for these top-like reconstructions, the attenuations are really more substantial. So as much as 30-fold or so attenuated from uniform. So what are the properties of the SCF value? Well, the SCF describes quantitatively the geometry of the sampling distribution. So that means how uniform it is. It scales between 0 and 1. We argue that it's directly related to experimental resolution as defined by the FSC or SSNR. So that means that an SCF of 1 has no effect on the global resolution. 0.5, there's a 2-fold attenuation. At 0.1, there's a 10-fold attenuation. It can take into account missing data. So if you don't have particles along viewing directions or zeros in the transform, you have to just correct for those zeros. But it can't take that into account. And what we were interested in what we've been interested in is really it lays the groundwork for predicting an optimal tilt angle for collecting data because most preferentially oriented samples have an SCF value of less than 0.5. What we started doing recently was representing sampling on the surface of a Fourier sphere. So what do I mean by that? Well, if this is your projection distribution, this is a sampling map, and it's just thresholded really, really low. So you can see that most of the near the XY plane is sampled, and you have missing information, perhaps some slices here, but attenuated information along so axially. And what we've been doing is we've been just taking we've been plotting histograms of sampling along with the surface of a sphere that's taken from this transform, and it's approximately invariant to where you take it in terms of distance from the origin. So because the sampling scales as 1/k, but the patterning of the sampling remains approximately constant within a certain regime. And so we started plotting those on the surface of these spheres. So what this is, it's just a histogram of sampling values plotted on the surface of a sphere. And so you can see that there's a lot of sampling near the XY plane, but then you get less sampling in the axial regions. And the advantages of these so-called surface sampling plots is that it's a representation of non-uniformity at the level of actual sampling rather than from Euler angles themselves. Sometimes it's difficult to understand or to figure out whether or not a reconstruction is going to be good or bad just by looking at the Euler angles. But this is a representation at the level of the sampling of the reconstruction itself. You can use them to directly obtain an SCF value, as is shown here. And we argue that they're more informative or at least complementary to looking at Euler plots. All right, so how do these behave? So what do these look like for different sampling distributions? Well, this is a uniform distribution, okay? So these are side-like projections that I've already shown, and you can see that you have an accentuation of sampling along the z-axis, and then sort of a thinning as you go out. Here, you can introduce modulations in the phi angle, and those are accordingly displayed here. In red, you have some thinning according to those modulations. And then these are the top views. These are the ones that are really bad, where you have hypersampling near the XY plane, and then essentially no sampling along the z direction. And these also provide you with SCF values. In these cases, these are very, very good. These are very good reconstructions, but you can see in these two particular cases, now we get a really substantial attenuation of the SCF value. So how does one improve sampling? Well, a very simple way to do this is to just tilt the grid, as long as you don't have this nasty sort of denaturation or aggregation that's also caused by the air-water interface that tilting, of course, will not solve. But if you just have preferred orientation and not much or no denaturation of the sample itself, well, you could just tilt the grid in the microscope. the reason this works is because you end up sampling. The sampling always improves. So tilting alters the orientation distribution. It always improves the sampling, with the exception of the perfect case. It increases the SCF value. And so we show that here. So if this is a side-like distribution, it's an SCF value of 0.2. So if you tilt by 45 degrees, now that pushes this sort of this axial sampling. It pushes it out towards this, as this greater ring around the sphere. And you can see that the projections are also pushed, spread out, and the SCF value improves a little bit. It's already very, very good here, but it improves a little bit. For the side modulated case, if we tilt by 45 degrees, similar sort of phenomenon, but the SCF value now improves rather substantially. So it's about 15-fold or so improvement. And for the top-like cases, you end up also redistributing the projections, and effectively this, by tilting them 45 degrees, this ends up filling in much of the missing cone, and also a substantial improvement in the SCF. So we know that this works. We've shown this for a number of cases. Most samples that we don't have chameleon or spotted on, so we still freeze conventionally. For most samples, we're just now collecting tilted data, and because they're going to be preferred. So we show that it works. This is an untilted reconstruction. This is a tilted reconstruction. Now you can clearly see a lot of the features, the phosphates, and the drugs that we're interested in. We have a graphical user interface that we released for calculating surface sampling plots, SCF values. And that's available here on GitHub. All you need is an Euler angle file. So it's just the phi theta psi angle. So that's all you need. And you put those in, and you press calculate plots, and it gives you all these plots, as well as an SCF value. And then you have the slider bar, you can apply a tilt angle, and based on the tilt angle, you get these updated plots. And you can see that in this case, the SCF value goes up by almost 5-fold. So we think these are useful, but there is one important limitation right now in the current implementation. And that is that, and that's just shown here. So if you have an orientation distribution, such as the one that I've already introduced, characterized by theta of less than or equal to 30 degrees. Okay, so that gets an SCF value of 0.02. If you just take some of these particles from this orientation, from this data set, and you sprinkle them throughout the projections, the projection sphere. If you sprinkle them throughout, then the SCF value goes up by 5-fold. And likewise here, for this orientation distribution, the SCF goes up. And this is because you have better sampling. Okay, so we described this in last year's paper. I mean, this is because you have better sampling. But the problem is that in experimental cases, we always have these sprinkles. We always have false positive angular assignments. And so effectively what we're finding is that these SCF values that we're getting for experimental reconstructions are always a little bit elevated. And in some cases, they could be a lot elevated if you have a lot of, if you have a substantial amount of overfitting. So we think that there's a way to deal with this. We're still working on it, but on this idea, but we think that there's a way that we're going to be able to, correlate these sampling maps to 3D FSCs in order to deal with this sort of problem. So just to conclude, the sampling function, we argue, is a useful construction that's both relevant to directional and global resolution measures. These surface sampling plots, they're also useful to visualize how well the reconstruction is sampled. Bottom line is, the more isotropy, the healthier the resolution curves and better maps. And some of the challenges are to determine the effects of false positive angular assignments on the SCF, so to obtain these corrected sort of SCFs, to incorporate them into the workflows for refinement and reconstruction, and ultimately to use them to predict an optimal tilt angle for the data. Grigori, how much time do I have? Do I have a few minutes?
Yes, you still have 5 minutes.
Correct. So I just want to point on this note. So this is what we're interested in doing, is to use these ideas to predict an optimal tilt angle for any data set upon initiation. And of course, tilts can have problems. You have fundamentally you have thicker ice, but you also have focus gradient, and you have more beam-induced movement. What we've been doing is we've been trying to figure out how to deal with these sorts of problems computationally. And essentially what we did is we took isotropic cases, fully sampled isotropic particles, and we collected data sets at different tilt angles ranging from 0 to 60 degrees. And at first, when we started processing the data, they behaved as one would expect. The 60 degree data sets were by far the worst. They had the worst resolution. But then after we started implementing some of these novel ideas implemented in Reliant and PrioSpark, and iterating through CTF refinement, Bayesian polishing, and so forth, now we're at a point where the reconstructions from untilted and tilted data sets are essentially very, very similar. So this is AAV at 2.08 from untilted and at 60 degrees from 60 degree tilted data. We also did this for a small particle, so it's not just something big like AAV. It's also, we also did it for DPS. And for DPS now, you do get a little bit of attenuation, but it really isn't that substantial. And actually, I just, this is an idea that also Dmitry Teganov brought up in his recent paper, that in principle, there shouldn't be that much of a difference between just single particle and tomographic tilt series. This isn't a tilt series, it's tilted single particle data, but similar sort of concept. So our hypothesis is that most, not all, but most of the problems that are associated with tilts could be ameliorated using these computational strategies. And now with that, I just want to acknowledge much of this work is really the wonderful work of Phil Baldwin, who was a physicist in the lab. Young Zitian has been doing some of the experimental work. He's been a longstanding collaborator with the lab, also a graduate student with Bridget, and then Sri in my lab has been contributing with some protocols and collaborators. Thanks.
Thank you very much, Dmitry, for a really wonderful talk. We have one question. How does SCF compare to the Cryo-EM program, which evaluates points per function and suggests a tilt angle as well?
Yeah, it's so, I mean, there are some similarities between the two. We think that the SCF is because it's derived from first principles, it's more useful. It has a logical scale from 0 to 1. So we think it's going to be more useful. The problem right now is that, like I brought up, there's a little bit of elevation, but we actually see some correspondence, quite a bit of correspondence when we compare reconstructions using the two, or the Euler plots.
Okay, thank you very much. I think we will wrap up now, and I'd like to thank you again for the talk. And now I'll pass the speaker to Olga Sokolova, who will make a short announcement.
Hello again, dear participants and speakers. I would like to thank all speakers today. It was a great first day of the conference, and tomorrow we will continue in hybrid format. That means some talks will be in not on a Zoom, but in person. So we will meet all speakers in Center of Bioengineering. So some people who cannot come to Center of Bioengineering, they will speak through the Zoom like today, but some people will speak in person. So we're looking forward to meeting them. And today, in 1 hour, we will meet you at Moscow State University Botanical Garden, where we will hold a welcome party. Okay, thank you again. So see you all tomorrow.